For countless generations, human beings have lifted their eyes to the night sky, captivated by the glittering expanse above, and asked themselves the same profound question: what lies out there? And beyond mere curiosity, there has always been a deeper, more pressing wonder. How far can we truly journey into the cosmic abyss? From the triumphant first steps on the moon to the intricate robotic landings on Mars, humanity has gradually begun to extend its reach into the vast and seemingly infinite ocean of the universe. Yet, when measured against the immensity of the cosmos, these achievements are barely the gentlest of touches, a mere toe dipped into the unending waters of space. One cannot help but ponder, what would it mean to venture farther still? Could humans one day travel beyond the comforting boundaries of our solar system? Could we ever set foot around a distant star? Or perhaps even traverse the unimaginable reaches of another galaxy? And what obstacles might lie in our path? Technological limits, the constraints of time, the frailty of human biology, or some other challenge yet unseen? In order to even begin to answer these questions, we must first understand the vast distances we are contemplating. A light year, sometimes simply called a light year, is not a measure of time, despite its potentially misleading name. Instead, it is a unit of distance, one that describes how far light can travel in the span of a single year. And because light travels at the fastest speed known in the universe, this distance is almost beyond comprehension. According to the International Astronomical Union, 1 light year corresponds to the distance light traverses in a vacuum over the course of a Julian year, which consists of 365 25 days. In precise figures, this translates to 9,460,703,458,258.88 kilometers. For those more accustomed to miles, that equals roughly 5,880 billion miles. Numbers so vast, they defy ordinary human intuition. While professional astronomers often prefer an alternative unit called the parsec, equivalent to about 3.26 light years, the concept of the light year has captured the popular imagination, frequently appearing in books, documentaries, and casual discussions about the stars, galaxies, and the nearly incomprehensible scale of the universe. The idea of using light years as a unit of measurement first gained traction in the 19th century, after the German astronomer Friedrich Bessel made a groundbreaking determination in the year 1838. He successfully measured the distance to a star beyond our sun, known as 61 Cygni, using an instrument called a heliometer, which featured a lens 6.2 inches wide and was crafted by the renowned optician Joseph von Fraunhofer. At that time, the largest unit commonly used to describe cosmic distances was the astronomical unit. The average gap between Earth and the Sun, which is about 150 million kilometers or 93 million miles. Using a technique called trigonometric parallax, Bessel calculated that 61 Cygni was roughly 660,000 astronomical units away. In other words, the light we see from that distant star today began its journey toward Earth more than 10 years ago. Although Bessel referenced the time light would take to reach us, he did not adopt light years as a formal unit, likely because the speed of light had not yet been determined with sufficient precision, and incorporating it could reduce the accuracy of his calculations. Throughout the mid-19th century, scientists worked diligently to refine their measurements of light's speed. In 1849, Hippolyte Fizeau offered a more precise estimate, later improved in 1862 by Léon Foucault. During this era, the behavior of light remained a profound mystery, complicated by the once popular hypothesis of a cosmic ether filling the void of space. The term light year first appeared in print in 1851 in a German article by Otto, who likened it to expressions such as a walking hour, representing the distance one can travel on foot in a single hour. By 1868, the term had appeared in English publications, noted as a German unit of measurement. While some scientists, including the esteemed British astrophysicist Arthur Eddington, criticized it as imprecise or irrelevant, the light year had firmly entered both popular science and scientific discourse. Today, light years remain an indispensable tool for visualizing the staggering distances separating stars and galaxies. They allow us to imagine the enormity of space. Typical galaxies may span from a few thousand to hundreds of thousands of light years, while the gaps between galaxies and clusters extend across millions of light years. Some of the most remote cosmic phenomena, including quasars and structures like the Sloan Great Wall, exist billions of light years away. Within the more intimate confines of a star system, such as our solar system, however, distances are far smaller, usually expressed in astronomical units rather than light years. Beyond the light year, scientists use additional units based on the speed of light to describe shorter distances. A light second represents how far light travels in a single second, roughly 299,792,458 meters. A light minute equals 60 times that distance, with light hours and light days following the same pattern. Even a light month exists, defined as the distance light travels in 30 days. Remarkably, light covers nearly 1 foot in just a nanosecond, a billionth of a second, a concept whimsically referred to by some as a light foot. Another crucial unit, the parsec, is specifically used by astronomers to determine the distances to stars and galaxies well beyond our solar system. 1 parsec equals approximately 3.26 light years, or 26,265 astronomical units, which translates to around 30.9 trillion kilometers, or 19.2 trillion miles. The parsec emerges from the principle of parallax combined with basic trigonometry. By observing a star from 2 different vantage points and measuring how its position appears to shift, astronomers can define a parsec as the distance at which 1 astronomical unit subtends an angle of 1 arcsecond, a minuscule fraction of a degree, 1 part in 3,600. To visualize this, imagine an elongated triangle extending across space. One short side represents the distance from Earth to the Sun, while the vertex opposite that side forms an angle of 1 arcsecond. The other side, stretching far into space, defines 1 parsec. For context, the closest star beyond our Sun, Proxima Centauri, is approximately 1.3 parsecs away, roughly 4.2 light years. From that distance, the span of Earth's orbit around the Sun appears infinitesimally small. Most stars visible to the naked eye lie within a few hundred parsecs, while the most distant can be several thousand parsecs away, and the Andromeda Galaxy itself is over 700,000 parsecs from our vantage point. The term parsec, a fascinating contraction of parallax of 1 arcsecond, was first coined in the year 1913 by the British astronomer Herbert Hall Turner. His goal was simple yet profound: to make the formidable challenge of measuring cosmic distances a bit more manageable. In those early days of modern astronomy, the distances to stars and galaxies were so vast that traditional units like miles or kilometers were almost meaningless, lost in a haze of unimaginably large numbers. By introducing the parsec, Turner provided astronomers with a practical, precise tool for quantifying the immense reaches of space. Today, professional astronomers continue to rely on parsecs for the meticulous work of mapping the cosmos. Yet, when it comes to sharing the grandeur of the universe with the public, light years remain the star of the show. They help convey, even if in a rough sense, the almost incomprehensible scale of the universe beyond our pale blue dot. However, in popular science books, documentaries, and public lectures, light years still dominate conversations. The term is familiar, intuitive, and carries with it a sense of cosmic wonder. But astronomers often require something more precise when dealing with the staggering distances between stars and galaxies. This is where multiples of the parsec come into play. A kiloparsec, or 1,000 parsecs, is used to describe distances within and around our own galaxy, the Milky Way. When reaching farther, astronomers employ megaparsecs, representing 1 million parsecs, to chart galaxies that lie far beyond our immediate stellar neighborhood. For the most distant reaches of the universe, including quasars and galaxies at the very edge of what we can observe, gigaparsecs, 1 billion parsecs, become the necessary scale. The International Astronomical Union, the IAU, formalized the definition of a parsec in August of 2015. They declared that 1 parsec is exactly 648,000 divided by pi astronomical units. Taking into account the IAU's precise definition of the astronomical unit from 2012, this means 1 parsec measures roughly 30.9 trillion kilometers. To visualize how this astonishing figure arises, imagine a skinny triangle stretching across space. One side represents the distance from the Earth to the Sun, and the angle opposite it measures precisely 1 arcsecond. Using trigonometry, the elegant mathematics of triangles, astronomers can calculate the length of the far side of this cosmic triangle. That distant side turns out to be 1 parsec. One of the oldest and most ingenious techniques for gauging stellar distances relies on measuring a star's apparent shift against the background of more distant stars. Observers take a measurement when Earth is on one side of the Sun, then wait roughly 6 months until our planet has journeyed to the opposite side. Over this time, Earth's motion spans twice the distance between Earth and the Sun. The resulting tiny apparent shift of the star, known as the parallax angle, allows astronomers to compute its distance with simple trigonometry. The first successful measurement of a star's distance in this way occurred in 1838 when German astronomer Friedrich Wilhelm Bessel determined the distance to the star 61 Cygni. He found it to be about 3.5 parsecs away, a groundbreaking achievement that demonstrated the power of parallax for understanding the scale of the cosmos. Imagine standing on Earth and watching a nearby star as our planet orbits the Sun. As we move, the star seems to jiggle slightly against the backdrop of distant stars. This tiny apparent motion is parallax, defined precisely as half the angle through which the star appears to shift over 6 months. Another way to picture it is to imagine a massive triangle stretching from Earth at one point in its orbit to the Sun at the center and extending out to the distant star. The parallax angle is the angle seen from the star between Earth's 2 positions. So small is this angle that astronomers measure it in arcseconds, with 3,600 arcseconds comprising a single degree. Replacing that 1 arcsecond angle in the cosmic triangle with the measured parallax of a star gives the distance to that star from the Sun. When a star's parallax angle equals 1 arcsecond, its distance is precisely 1 parsec. A parsec, in essence, is a unit derived directly from parallax. Its very name blends the concepts of parallax and arcsecond. 1 parsec represents the distance at which the space between Earth and the Sun would appear as a single arcsecond. Translated into more tangible terms, this works out to roughly 3.26 light years. The beauty of using parsecs for astronomical measurements lies in their simplicity. If a star exhibits a parallax of 1 arcsecond, it is 1 parsec away. If the parallax is half an arcsecond, the distance doubles to 2 parsecs. If it measures 1/10 of an arcsecond, the star lies 10 parsecs distant. For such minuscule angles, basic triangle approximations suffice, bypassing more complex trigonometry. The word parsec first appeared in scientific literature in 1913. At the time, astronomer Royal Frank Watson Dyson advocated for a proper name for this crucial distance unit. While Dyson suggested astron and another scientist, Carl Cheria, proposed cerometer, it was Herbert Hall Turner's term parsec that ultimately prevailed, becoming the standard in astronomy. Despite its utility, the parallax method has limits. Earth-based telescopes can measure parallax angles only down to roughly 1/100th of an arcsecond, restricting accurate distance calculations to about 100 parsecs. Atmospheric turbulence blurs the images of stars, limiting precision. Space telescopes, freed from the distortions of our atmosphere, overcome this hurdle. Between 1989 and 1993, the European Space Agency launched Hipparcos, a satellite capable of measuring the positions of around 100,000 stars with nearly 1,000th of an arcsecond accuracy, extending distance measurements up to 1,000 parsecs. Decades later, on December 19, 2013, ESA launched Gaia, a space observatory of unprecedented capability. Gaia is designed to measure distances to approximately 1 billion stars with accuracy down to 20 micro-arcseconds. This precision allows astronomers to gauge distances with just 10% error even to the center of our galaxy, roughly 8,000 parsecs away toward the constellation Sagittarius. Putting these distances into perspective illuminates their vastness. The distance from the Sun to Earth, 1 astronomical unit, is just under 5 millionths of a parsec. Voyager 1, humanity's farthest traveling spacecraft as of February 2024, has reached approximately 0.00079 parsecs after 46 years of journeying. The Oort cloud, a vast shell of icy bodies encircling our solar system, spans around 0.6 parsecs. When astronomers discuss distances between stars, parsecs are the standard measure. For larger scales, like distances across galaxies or between them, kiloparsecs, 1,000 parsecs, become useful. Some specific examples highlight the cosmic scale. Proxima Centauri, the nearest known star to our Sun, lies about 1.3 parsecs, or roughly 4.24 light-years away. The Pleiades star cluster is around 130 parsecs distant, roughly 420 light-years. The center of our Milky Way galaxy is more than 8,000 parsecs, about 26,000 light-years from our Sun. Our galaxy itself stretches across 34,000 parsecs, or roughly 110,000 light-years, a span so vast it defies ordinary comprehension. The parsec, humble in name but monumental in scope, remains one of the cornerstones of our understanding of the universe, allowing us to chart distances in a cosmos that continues to astonish and inspire. One of the most awe-inspiring cosmic giants ever observed is the galaxy known as ESO 383-76. Its sheer scale boggles the mind, stretching across an estimated diameter of approximately 540.9 kiloparsecs, which translates to nearly 1.8 million light-years. To place this in perspective, consider our nearest substantial galactic neighbor, the Andromeda Galaxy. Situated at a distance of roughly 780 kiloparsecs, or about 2.5 million light-years from Earth, Andromeda serves as a kind of cosmic mirror to our own Milky Way, though it is dwarfed by the enormous proportions of ESO 383-76. Astronomers often describe these mind-boggling distances using a specialized unit called the megaparsec. 1 megaparsec is equivalent to 1 million parsecs, which in turn corresponds to about 3,260,000 light-years. This unit allows scientists to communicate the staggering expanses separating galaxies, clusters, and superclusters without constantly resorting to numbers so large they become unwieldy. Even light, which travels at an incredible 300,000 kilometers per second, would take millions of years just to traverse these distances. Sometimes, distances are expressed in terms such as 50 over 8 megaparsecs or 50 megaparsecs to the power of -1. This can seem perplexing at first glance, but it involves a helpful mathematical tool known as the Hubble constant, often represented by a dimensionless letter h. This number compensates for uncertainties in the precise rate at which the universe expands. Typically, h falls somewhere between 0.5 and 0.75, relating directly to the actual Hubble constant, which measures how quickly galaxies are receding from us. Using this, astronomers can estimate distances from the observed redshift, the stretching of light as galaxies move away, through a formula combining the speed of light, the Hubble constant, and the redshift value itself. When venturing into even more colossal scales, scientists employ the gigaparsec, a unit equivalent to 1 billion parsecs, or roughly 3,260,000,000 light-years. This is the scale needed to discuss some of the universe's largest structures, such as the CFA2 Great Wall, a vast assembly of galaxies stretching across unimaginable distances. In fact, a single gigaparsec spans nearly 1/14 of the observable universe, which is bounded by the faint glow of the cosmic microwave background radiation, the oldest light detectable from the early universe. To illustrate these scales, consider a few examples. Andromeda, our nearest galactic companion, sits about 0.78 megaparsecs away, or 2,500,000 light-years. The Virgo cluster, the closest significant cluster of galaxies, is located around 16.5 megaparsecs, or 54 million light-years from Earth. RxJ1242-11, a galaxy harboring a supermassive black hole similar to the one anchoring our Milky Way, lies some 200 megaparsecs away, roughly 650 million light-years. And stretching across 3 gigaparsecs, the Hercules Corona Borealis Great Wall, discovered in November of 2013, spans nearly 9,800,000,000 light-years, making it one of the largest structures known. The farthest reaches observable, the edge of the universe, extend about 14 gigaparsecs away, translating to around 46 billion light-years. Astronomers estimate the number of stars in our Milky Way by analyzing 3-dimensional sections of space in various directions. These volumes, measured in cubic kiloparsecs, allow scientists to count stars within each cube and extrapolate totals across the galaxy. Using similar methods, they estimate the numbers of globular clusters, tightly bound collections of stars, dust clouds, and interstellar gas. When surveying superclusters, measurements shift to cubic megaparsecs, tallying galaxies and categorizing them to extrapolate the grand total across the observable universe. Enormous voids, such as the Buddha void, are also measured in these massive units, highlighting the staggering emptiness of some cosmic regions. Physical cosmology, the study of the universe at the largest scales, employs cubic gigaparsecs to map how matter, galaxies, and luminous phenomena like quasars are distributed. Even within our local neighborhood, these measurements reveal remarkable variations. The space surrounding the Sun, roughly 1 cubic parsec in volume, contains only the Sun itself, a solitary star amidst vast emptiness. By contrast, globular clusters can cram 100 to 1,000 stars into a single cubic parsec, demonstrating the incredible diversity of stellar environments. When studying gravitational waves, subtle ripples in spacetime caused by cataclysmic events like black hole collisions, observatories such as LIGO and Virgo describe the volumes they monitor in cubic megaparsecs. These cubes grow with the reach of the detectors, representing vast regions of the cosmos listened to for these faint disturbances. Turning closer to home, the Moon, Earth's steadfast companion, has orbited our planet for billions of years at an average distance of about 384,000 kilometers, or roughly 238,000 miles, about 30 times Earth's diameter. Its orbital period is synchronized with its rotation, taking approximately 29.5 Earth days, which causes the same lunar hemisphere to perpetually face us. The Moon's gravity, though just over 1/6 that of Earth, exerts a crucial influence on our planet, primarily governing ocean tides. With a mass about 1.2% that of Earth and a diameter of 3,474 kilometers, roughly the width of the mainland United States, it is the largest natural satellite relative to its parent planet in the solar system. Composed of rock similar to Earth's crust, the Moon lacks an atmosphere, liquid water, and a magnetic field. Its formation is widely believed to stem from a colossal collision around 4.5 billion years ago, when a Mars-sized body named Theia struck Earth. The resulting debris coalesced over time to form the Moon. Its surface, a blend of towering mountains, deep impact craters, long rills, and dark plains called Maria, tells a story of a violent and dynamic past. Despite appearing luminous in the night sky, the Moon reflects only about as much light as asphalt. Its apparent size nearly matches the Sun's, allowing it to perfectly obscure the solar disk during a total eclipse. Subtle wobbles in its orbit, known as librations, allow observers to glimpse roughly 59% of its surface over time. Throughout human history, the Moon has inspired myths, art, religion, and science. It was the first extraterrestrial body approached by spacecraft, beginning with the Soviet Luna missions in the late 1950s and 60s. On July 20th, 1969, Apollo 11 landed in Mare Tranquillitatis, marking humanity's first footsteps on another world. Subsequent missions extended our exploration, culminating in Apollo 17, which set a record for the longest stay on the lunar surface at 75 hours. Plans for robotic and crewed missions continue to evolve, ensuring the Moon remains a focal point of human curiosity. The Moon's name in English, capitalized as Moon, derives from the Old English Mona, tracing back through Proto-Germanic and Proto-Indo-European roots meaning month, reflecting the way early humans measured time by lunar cycles. In classical literature and mythology, the Moon has been called Luna, Cynthia, and Selene, the latter from Greek mythology where Selene was the goddess of the Moon, and Cynthia referencing Artemis, the Greek lunar deity. The term lunar and the rarer Selenic or Selenian describe objects or phenomena associated with the Moon. Even scientific terminology, such as the element selenium and the field of selenography, derives from these ancient linguistic roots. Lunar geology divides the Moon's history into periods defined by crater types and lava plains. Some of the youngest, like Copernicus and Tycho, still display prominent rays of ejected material. By analyzing lunar rocks returned to Earth, scientists estimate that the Moon formed roughly 50 million years after the birth of the solar system. Although numerous theories have been proposed, ranging from the moon being spun off Earth due to rapid rotation captured as a wandering body or co-formed alongside Earth, none explain all observations as convincingly as the giant impact hypothesis, which accounts for the moon's lower metal content and orbital characteristics. The moon remains not just a celestial body, but a gateway to understanding planetary formation, gravitational dynamics, and humanity's place in the universe, a silent witness to the cosmos unfolding over billions of years. And so the story of the Earth-Moon system begins not with calm, but with chaos, a moment of cosmic violence that forever altered the architecture of our solar system. Today, the idea that dominates scientific thought is known as the giant impact theory. It provides the most compelling explanation for the extraordinary energy locked within the Earth-Moon duo and the remarkably intricate bond they share. According to this prevailing theory, over 4.5 billion years ago, when the Earth was still a tender, forming world, a colossal celestial body roughly the size of Mars, later named Theia, collided with it. The collision wasn't a direct head-on strike, but rather a glancing blow, a near miss that unleashed a titanic storm of molten rock and debris into the vast emptiness of space. This ejected material did not simply vanish. It hovered in a precarious orbit just beyond a boundary now called the Roche limit, a distance roughly 2.5 times the Earth's radius. Over countless years, gravity orchestrated a slow and intricate dance, drawing the scattered fragments together, eventually giving rise to the moon as we know it today. In the early solar system, collisions of this magnitude were surprisingly common, and modern computer simulations have painstakingly recreated these events, producing results that astonishingly align with the moon's current mass, core structure, and orbital behavior. Intriguingly, initial models suggested that the majority of the moon's substance originated from Theia rather than the Earth itself. Yet, as science evolved, particularly around the year 2007, new simulations hinted that a far greater portion of the moon might have come from the Earth, challenging long-held assumptions. The plot thickens when we examine the elemental fingerprints embedded in planetary rocks. Samples from Mars and the asteroid Vesta reveal oxygen and tungsten isotopes that differ significantly from Earth's, yet the moon's isotopic composition mirrors our planet almost perfectly. This perplexing similarity poses a conundrum. If the moon was largely Theia's offspring, why do its atoms echo Earth so closely? One elegant hypothesis proposes that the cataclysmic impact produced a vast, vaporized shroud of molten rock surrounding both Earth and the nascent moon, thoroughly mixing their material and erasing any distinct chemical signatures. However, the debate is far from settled, and many scientists continue to explore alternative explanations. The sheer force of the impact unleashed an extraordinary amount of energy, melting the outer layers of both bodies and creating oceans of searing magma. The moon's own molten layer may have reached depths between 500 and 1,700 kilometers, forming a churning, incandescent sea of rock. Even today, the giant impact theory accounts for much of the observed dynamics between the Earth and Moon, yet questions linger. For example, the moon's composition still holds mysteries. If significant material originated from Earth, certain chemical markers like zirconium, silicon, and oxygen isotopes do not fully reconcile with existing data. Cutting-edge simulations published in 2020 using over 100 million virtual particles demonstrated that a moon-like satellite could form nearly instantaneously after such a violent impact. Even if the fledgling moon started perilously close to the Earth inside the Roche limit, it could survive and eventually stabilize into a distant orbit. More recent models, released in early November 2023, propose that remnants of Theia may still lie buried deep within the Earth, vestiges of a primordial collision frozen in time. Initially, the moon orbited much closer to Earth than it does today, appearing enormous in the sky, while Earth itself would have loomed large from the moon's surface. Eclipses were frequent, and the gravitational pull between the two bodies was tremendously powerful. Over the eons, tidal forces gradually nudged the moon outward, elongating its orbit and slowly moderating the pull between the two. As the moon cooled, it lost most of its tenuous atmosphere, and countless impacts, both large and small, sculpted its cratered terrain. Remarkably, volcanic activity persisted until roughly 1,200,000,000 years ago, forging the dark plains known as the Lunar Maria. The bulk of this volcanism occurred between 3,300,000,000 and 3,700,000,000 years ago, with some lava flows as ancient as 4,200,000,000 years, and others as young as 1,200,000,000 years. Curiously, much of this volcanic activity is concentrated on the side of the moon facing Earth, likely because the crust there is thinner, allowing magma to breach the surface more readily following massive impacts. The moon's shape is far from perfectly spherical. Earth's gravitational influence stretches it slightly, creating a form known as a scalene ellipsoid. Its longest axis, however, does not point directly toward Earth, deviating by roughly 30 degrees, a distortion attributed to ancient impact basins. The moon remains more elongated than contemporary gravitational forces alone would dictate, suggesting that its current form is a fossilized imprint from a time when it was molten and far closer to Earth. Despite its relatively modest size, the moon is substantial when compared to other natural satellites. With a diameter of roughly 3,500 kilometers, over a quarter of Earth's width, it spans a surface area nearly 38 million square kilometers, comparable to the combined continents of North and South America. It is the fifth largest satellite in the solar system, and relative to its parent planet, the largest. Its mass constitutes roughly 1/81st of Earth's, giving it a surface gravity approximately 1/6 that of Earth. Escaping its pull requires a velocity exceeding 8,600 kilometers per hour. Beneath its surface, the moon reveals a layered internal structure reminiscent of Earth's. At its core lies a solid iron-rich center, around 240 kilometers across, surrounded by a liquid outer core nearly 300 kilometers thick. Encasing this is a partially melted mantle, roughly 500 kilometers deep. These layers emerged as the moon's exterior cooled while the interior remained incandescent. Denser minerals sank to form the mantle, lighter minerals floated to create the crust, and rare elements became trapped between these layers. Lunar orbital mapping confirms a crust dominated by light-colored anorthosite, and rock samples brought back by astronauts verify a mantle richer in iron than Earth's. On average, the crust is 50 kilometers thick, while the dense inner core spans a mere 350 kilometers, roughly 1/5 of the moon's overall diameter. Pressures at the center reach about 5 gigapascals, nearly 49,000 times the atmospheric pressure at sea level on Earth, and evidence suggests that portions of the core remain molten. Walking on the moon, one would feel an otherworldly lightness, subject to only 1/6 of Earth's gravity, around 1.62 meters per second squared, half of what one would experience on Mars. Yet even this weak gravity is uneven across its surface. By observing shifts in radio signals from orbiting spacecraft, a phenomenon known as the Doppler effect, scientists discovered regions of anomalously high gravitational pull, or mascons, concentrated near giant impact basins. These areas are laden with dense volcanic basalt that flowed in eons ago, leaving a lasting imprint on the moon's gravity that remains detectable to this day. But these dense lava flows, while certainly impressive in their scale and persistence, do not fully account for the mysterious excesses in the moon's gravitational pull observed in certain regions. These gravitational highs, known as mascons, continue to confound scientists because some of them appear in areas where there is no trace of volcanic activity at all. The mystery deepens with each observation, reminding us that our closest celestial neighbor still harbors secrets that challenge our understanding of planetary formation and evolution. And when it comes to magnetism, the moon is astonishingly quiet. Unlike Earth, which boasts a robust global magnetic field generated by its molten iron core, the moon's magnetic field is almost negligible, less than 0.22 nanoteslas, over 100,000 times weaker than our planet's. Its magnetic presence is not uniform across its surface. Instead, only certain patches of the lunar crust exhibit magnetization. Scientists believe these localized fields are remnants from a time billions of years ago when the moon may have sustained its own magnetic dynamo, a mechanism similar to Earth's, powered by the movement of molten metal within its core. Around 4 billion years ago, this dynamo could have generated a field as strong as Earth's is today. But over immense spans of time, as the moon's core cooled and solidified, this dynamo gradually ceased, likely vanishing completely around 1 billion years ago. Some residual magnetism might also have been imparted through violent cosmic events. Powerful impacts, which blasted large amounts of material into space, could have produced expanding clouds of plasma interacting with existing magnetic fields. Interestingly, the strongest magnetized regions on the moon today are often found opposite the sites of its largest ancient asteroid impacts, lending weight to the idea that these collisions played a role in shaping its magnetic character. Now, the moon's atmosphere, or more accurately, its near absence, is equally extraordinary. Unlike Earth's thick, life-supporting blanket of gases, the moon's atmosphere is so tenuous that scientists call it an exosphere. Its total mass is less than 10 tons, with a surface pressure that barely registers, around 3 times 10 to the power of -15 atmospheres, or a mere 0.3 nanopascals. This ultra-thin veil fluctuates subtly between lunar day and night. The gases that do exist in this ephemeral exosphere originate from 2 main sources. First, outgassing from deep within the moon itself slowly releases volatile compounds. Second, sputtering occurs when charged particles from the solar wind collide with the lunar surface, knocking atoms into space. Observations reveal the presence of sodium and potassium, alongside helium-4 and neon captured from the relentless bombardment of the solar wind. Radioactive decay beneath the surface adds other gases, including argon-40, radon-222, and polonium-210. Curiously, elements abundant in the lunar soil, such as oxygen, carbon, and hydrogen, rarely appear in the atmosphere, and the reasons for their absence remain a scientific enigma. Water, surprisingly, has also been detected, not pooling in lakes or rivers, but as vapor within the exosphere, especially concentrated between 60 and 70 degrees latitude. Scientists suggest this may arise from ice buried beneath the surface, sublimating directly into vapor when sunlight warms it. Yet even these gases are transient. Some are pulled back toward the lunar surface by gravity, while others drift away into space, either pushed by solar radiation or carried off by the solar wind when electrically charged. But the moon wasn't always this barren. Apollo mission rock samples reveal that between 3 and 4 billion years ago, the moon sustained a much denser atmosphere for approximately 70 million years. Volcanic eruptions of astonishing magnitude released immense quantities of gas, creating an atmosphere possibly twice as thick as Mars today. Gradually, however, the solar winds stripped this atmosphere away, leaving only the tenuous exosphere we observe now. Floating above this barren surface is a permanent cloud of dust, a silent testament to the constant cosmic bombardment. Roughly 5 tons of material strike the lunar surface every day from comets and meteoroids, sending fine dust particles into the air. Each particle can linger for about 10 minutes, rising for 5 and then settling for 5. At any given moment, approximately 120 kilograms of this dust hang suspended up to 100 kilometers above the surface, forming a cloud that is denser along the lunar terminator, the dividing line between day and night. Meteor showers like the Geminids or Quadrantids amplify this phenomenon, filling the skies with even more dust. Radiation adds another layer of harshness to lunar life. The sun, cosmic rays, and neutron radiation expose the moon to around 1.37 millisieverts per day during daylight hours. This is roughly 2.5 times what astronauts face aboard the International Space Station, 5 to 10 times more than passengers on a long-haul airplane, and 200 times higher than the average on Earth's surface. For perspective, a journey to Mars would expose travelers to about 1.84 millisieverts daily, while standing on Mars itself would mean about 0.64 millisieverts per day. The sun's energy also charges the dust, making it cling to surfaces and float in the lunar air, a phenomenon that could wreak havoc on machinery or pose serious risks to astronauts' lungs if it infiltrated habitats or suits. Lastly, the moon's axial tilt is minimal, just over 1.5 degrees compared to Earth's 23. This slight inclination means that the moon experiences no real seasons. However, it gives rise to astonishing phenomena. Certain high-altitude regions near the lunar North Pole, like the rim of Peary Crater, enjoy almost perpetual sunlight. These peaks of eternal light are prime candidates for future lunar bases, promising near-constant solar energy. The moon's surface experiences extremes beyond anything on Earth. Temperatures swing from blazing heat in direct sunlight up to about 120 degrees Celsius to freezing cold in shadowed regions, dropping to around minus 71 degrees Celsius. Without an atmosphere to mediate these swings, the topography itself, hills, valleys, and craters, dictates thermal conditions. Polar craters, perpetually shielded from the sun, rank among the coldest spots in the solar system. NASA's Lunar Reconnaissance Orbiter measured summer temperatures in southern polar craters as low as 35 Kelvin or minus 238 degrees Celsius, with northern craters like Hermit plunging to 26 Kelvin, around minus 247 degrees Celsius, colder than Pluto's surface. Covering the moon is a dusty, fragmented blanket called regolith. Formed over billions of years of relentless meteoroid impacts, regolith consists of pulverized rock, gray and powdery, resembling fine snow. Astronauts describe its smell as reminiscent of burnt gunpowder. Thickness varies. Older highlands have up to 10 to 15 meters, while smoother Maria regions average 4 to 5 meters. Beneath this lies megaregolith, a deep layer of fractured rock extending many kilometers below. The moon's harsh conditions, vacuum, radiation, and extreme temperatures render it highly unlikely that any Earth-borne bacteria could survive for more than a single lunar orbit. Over decades, scientists have meticulously mapped the moon's surface using laser ranging, stereo imaging, and orbital observations, slowly piecing together the story of a world both starkly desolate and endlessly fascinating. A silent companion that continues to challenge our understanding and ignite our imagination. One of the most awe-inspiring and remarkable landscapes in our celestial neighborhood lies on the far side of the moon, the South Pole Aitken Basin. This colossal impact crater stretches across an astonishing distance of about 2,240 kilometers, nearly 1,390 miles, making it not only the largest crater on the moon, but also the second largest confirmed crater in the entire solar system. Its scale is staggering, yet its depth is equally extraordinary, plunging some 13 kilometers or just over 8 miles beneath the surrounding surface. Within this immense basin, a smaller crater holds the very lowest point on the lunar surface, dipping over 9 kilometers below the moon's average elevation. By contrast, the moon's highest point, often referred to as the Selenian summit, rises more than 10 kilometers, roughly 6.5 miles, above the average surface, standing northeast of the South Pole Aitken Basin. Scientists theorize that the colossal impact responsible for carving the basin may have thrust this elevated region skyward, creating a dramatic juxtaposition of extremes. Other massive craters, such as Imbrium, Serenitatis, Crisium, Smithii, and Orientale, showcase similarly striking geological features, with deeply sunken centers contrasted by towering rims that rise sharply above the surrounding terrain. Interestingly, the far side of the moon, largely hidden from our earthbound view, sits on average about 1.9 kilometers, or roughly 1.25 miles, higher than the side we can observe. Adding another layer of complexity, the moon itself is slowly shrinking over time, a subtle process that has revealed itself through fault cliffs and surface cracks. These geological indicators suggest that the lunar surface has contracted by nearly 90 meters, or around 300 feet over the last billion years. As the moon cools gradually, its crust tightens and fractures, revealing an ongoing, if slow, evolution of its face. One region, named Mare Frigoris, long assumed to be geologically dormant, has recently shown evidence of cracking and surface movement, hinting at internal dynamics that continue to shape the lunar terrain. In 2010, the Lunar Reconnaissance Orbiter captured images of a particularly fascinating feature near the Sea of Tranquility, close to the famed Apollo 11 landing site, a cave marking the entrance of a collapsed lava tube. Measuring approximately 45 meters, or about 148 feet wide, and extending up to 80 meters, roughly 262 feet long, this subterranean chamber offers a stable interior temperature of around 17 degrees Celsius. In contrast to the moon's extreme surface temperatures, this temperate haven has sparked excitement among scientists and engineers as a potential location for future astronaut shelters, though reaching it remains fraught with risks such as falling debris or unstable ceilings. When gazing at the moon from Earth, the dark, smooth plains, once mistaken by early astronomers for seas, come into view. These plains, known as maria, are vast expanses of solidified lava, remnants of ancient volcanic eruptions that filled basins left by previous cataclysmic impacts. While the lunar lava bears resemblance to terrestrial basalt, it is richer in iron and largely devoid of minerals altered by water. Among these maria, the largest is Oceanus Procellarum, or the Ocean of Storms, notable for its apparent independence from any singular massive impact crater. As the lava cooled, it contracted, forming elongated ridges called wrinkle ridges, sometimes stretching hundreds of kilometers, which trace hidden structures buried beneath the surface. At the margins of maria, the cooling lava occasionally caused the ground to subside, creating arched cracks known as arcuate rills. Beneath the surface, ancient lava flows now concealed by debris from later impacts are referred to as cryptomaria, relics predating the maria we observe today. Similarly, some pools of impact-melted rock were later overlaid by lava, producing surface patterns distinct in brightness, texture, and placement from the surrounding flows. The moon also bears winding features called sinuous rills, believed to trace the paths of long-extinct lava rivers, or collapsed lava tubes. Typically beginning at volcanic vents, these sinuous formations meander across the lunar landscape, with some of the largest examples like Schroeder's Valley and Rima Hadley surpassing the size and complexity of similar structures on Earth. The twisting channels, complete with sharp bends and deep troughs, stand as enduring records of the moon's fiery past. Volcanism, particularly in the maria, has also reshaped numerous craters over time. Lava from the moon's interior has occasionally filled crater basins, lifting their floors and, under pressure, causing fractures to form. Craters such as Taruntius and Gassendi illustrate these processes, while others, including Huygens, arose purely from volcanic collapse rather than impact, forming smaller, uneven depressions lacking the raised rims typical of impact sites. On the near side of the moon, the hemisphere always visible from Earth, scientists have cataloged several shield and dome-shaped volcanoes, along with sites where explosive eruptions deposited ash, cinders, and thicker, stickier lava. The concentration of maria on this side is striking. They cover roughly 31% of the near side, compared to just about 2% of the far side. This disparity likely reflects differences in heat-producing elements beneath the crust, which cause the mantle beneath the near side to partially melt, sending lava to the surface. Most of these lava flows date back to the Imbrian period, between 3.3 and 3.7 billion years ago, though some eruptions may have occurred as recently as 1.2 billion years ago, with others originating as long as 4.2 billion years ago. In 2006, researchers identified exceptionally fresh, dust-free features in Lacus Felicitatis, suggesting volcanic events as recent as 2 million years, hinting at the moon's continued internal activity. Further evidence comes from 70 irregular mare patches, potentially less than 50 million years old, and recent activity within a crater inside the Orientale Basin, dated to 2 to 10 million years ago, suggesting pockets of residual warmth within the lunar mantle. The lighter regions of the moon, known as terra or highlands, form elevated terrains that are among the oldest surfaces, dating back roughly 4.4 billion years. Composed primarily of plagioclase-rich rock, these areas emerged when the moon's surface was still molten. Unlike Earth, the moon's mountains were not formed by tectonic shifts, and the uneven distribution of maria may be linked to differences in crustal thickness. The far side, particularly in highland areas, possesses a significantly thicker crust. One hypothesis posits that a smaller, ancient moon collided with the larger moon, accounting for this asymmetry. Another theory suggests that when the moon orbited closer to Earth, differential heating from our planet affected one side more than the other, creating lasting contrasts in interior warmth and surface evolution. This dynamic interplay of impact events, volcanic activity, and subtle tectonic adjustments paints a picture of a moon that is far from a static, lifeless body. Instead, it is a celestial archive, holding billions of years of cosmic history in its craters, plains, and hidden valleys, a silent witness to the tumultuous processes that have shaped not only itself, but the broader solar system. And so it begins, the story of the moon, a celestial body whose surface is a tapestry of time, chaos, and cosmic collisions. One of the most dramatic sculptors of this alien landscape is impact cratering, a relentless, silent force that has left its mark across billions of years. When asteroids, comets, or fragments of space debris strike the moon, they do so with unimaginable velocity, releasing energies that can reshape its surface in an instant. On the near side alone, astronomers estimate there are roughly 300,000 craters wider than a kilometer, each one a frozen record of violent encounters. Craters tell a tale of variety, a language of form shaped by size and circumstance. Small craters often appear as simple bowls with raised rims, neat in their geometry, while larger craters evolve into complex structures. Flat floors, terraced walls, and sometimes even central peaks rise from their centers like scars of the moon's ancient past. Beyond these, the moon hosts colossal multi-ring basins, concentric mountain chains surrounding a central depression, monuments to impacts of unimaginable scale. Yet not all craters adhere to perfect symmetry. Some are distorted, angular, or stretched, their shapes whispering secrets about fractures beneath the surface or unusual angles of impact. Craters such as Kaner and Janssen hint at underlying faults guiding the collapse of lunar soil, while elongated craters like Messier and Schiller may reveal impacts that arrived obliquely, shattered mid-flight, or occurred in twin strikes. Embedded in this chaotic landscape is the history of the moon itself. Scientists chart its story using the largest, most prominent craters, Nectaris, Imbrium, Orientale, as milestones marking epochs of cosmic violence. These monumental impacts scatter debris across the surface, layering it like pages in a geological book, allowing researchers to distinguish older regions from younger ones. Because the moon lacks weather, wind, or recent volcanic activity, many craters have remained remarkably well preserved for billions of years. By counting craters in a given area, scientists can estimate the age of the surface, though caution is needed. Large impacts can fling material far and wide, creating secondary craters that complicate the narrative. The rocks brought back by Apollo missions provide tangible timestamps. Impact melted stones date between 3.8 and 4.1 billion years, evidence of a tumultuous era known as the Late Heavy Bombardment. Modern eyes in the sky, like the Lunar Reconnaissance Orbiter, reveal that impacts are ongoing. Tiny collisions and ejecta from larger strikes churn the moon's topmost soil just 2 centimeters deep, roughly every 81,000 years, a pace far faster than earlier predictions based solely on micrometeorites. Yet, the moon's surface holds subtler mysteries as well. Lunar swirls, bright and curly patterns etched across the soil, appear newer than their surroundings and correlate with strong magnetic fields. Some lie directly opposite major impact sites, such as the famed Reiner Gamma swirl. Scientists suspect these luminous areas resist the relentless battering of the solar wind, preserving their brightness over eons. And then there is water, or rather, its ghostly traces. The moon is inhospitable to liquid water. Sunlight instantly breaks apart any exposed molecules, sending them into space. Yet for decades, researchers have suspected ice might survive in the eternal darkness of polar craters. These shadowed sanctuaries, frigid and untouched by sunlight, may harbor water delivered by comets or forged through reactions between lunar rock and solar hydrogen. Estimates suggest as much as 14,000 square kilometers, or about 5,400 square miles, of the moon could be cloaked in permanent shadow, a frozen reservoir awaiting discovery. Clues to water's presence have accumulated over decades. In 1994, radar data from Clementine hinted at small frozen patches near the poles. Later observations raised doubts, suggesting the radar reflections might be debris from young impacts rather than ice. In 1998, Lunar Prospector detected elevated hydrogen levels in the top meter of lunar soil, regolith, bolstering the water hypothesis. Even Apollo 15 samples, tiny volcanic glass beads, revealed minute amounts of trapped water, evidence that the moon's interior once held moisture. In 2008, India's Chandrayaan-1 mission made a pivotal advance. Its moon mineralogy mapper revealed light signatures consistent with hydroxyl and water molecules, with concentrations reaching up to 1,000 parts per million in some regions. Further analysis in 2018 confirmed water ice hidden in permanently shadowed craters at both poles. NASA's L-Cross mission in 2009 intentionally impacted a shadowed crater, ejecting at least 100 kilograms of water, with subsequent studies increasing the estimate to roughly 155 kilograms. Apollo 17's orange glass soil, formed during explosive eruptions about 3.7 billion years ago, contained melt inclusions with water concentrations comparable to Earth's upper mantle, tiny reservoirs deep beneath the surface that took decades and advanced instruments to detect. Later, in 2018, the Moon Mineralogy Mapper finally delivered the clearest confirmation yet. Water ice truly exists on the lunar surface, safely ensconced in craters that never see sunlight. Even more surprising, by October of 2020, molecular water was detected on the sunlit side, proving that the Moon's water is not confined to shadowed recesses. The Moon's story is inseparable from Earth. Together, they orbit a shared center of mass known as the Berry Center, located about 1,700 kilometers beneath Earth's surface. Its orbit is not a perfect circle, but slightly elliptical, with an eccentricity of 0.055, averaging 400,000 kilometers, or roughly 250,000 miles, between the two bodies. It completes a sidereal orbit in about 27.3 days, but because Earth and Moon move together around the Sun, the lunar phases span 29.5 days, a synodic month equal to one lunar day. The Moon keeps one face perpetually toward Earth, a consequence of tidal locking, yet subtle wobbles allow glimpses of nearly 60% of its surface over time. Unlike most moons, its orbit tilts toward the plane of Earth's solar path, a tilt compounded by the gravitational tug of both Earth and Sun, producing intricate motions. Cassini described these effects centuries ago, now known as Cassini's laws. Gravitational interplay between the Earth and Moon drives tides, not only in the oceans, but in the crust itself, which rises and falls about 10 centimeters during each lunar cycle. Some researchers even propose the Moon may help sustain Earth's magnetic field, a guardian against harmful solar radiation. Meanwhile, stresses built by constant gravitational pull trigger small moonquakes, quieter, gentler siblings to Earth's earthquakes, yet a reminder that the Moon is never truly at rest. And so, from violent impacts to secretive ice, from tidal dances to hidden tremors, the Moon emerges not just as a barren rock in the night sky, but as a dynamic, complex partner to Earth, holding stories that stretch back billions of years and secrets we are only beginning to unravel. However, what truly sets moonquakes apart from their terrestrial counterparts is their remarkable longevity, sometimes continuing for as long as a full hour. Unlike earthquakes on Earth, which tend to dissipate their energy relatively quickly, moonquakes persist because of the Moon's peculiar geological structure. The lunar surface, especially the upper crust, is dry, brittle, and fragmented into countless jagged pieces. When seismic vibrations travel through this fractured crust, they ricochet, bouncing endlessly from one fragment to another, taking far longer to fade than they would in the denser, more cohesive rocks found on Earth. This surprising behavior of the Moon was first revealed thanks to instruments called seismometers, carefully placed by Apollo astronauts during missions between 1969 and 1972. These devices, tiny sentinels left on the lunar surface, transmitted a wealth of data, opening humanity's eyes to a world of seismic activity previously thought impossible on our serene satellite. The Moon's influence, however, extends far beyond its occasional quakes. One of the most familiar and immediate effects of our celestial neighbor is the rhythmic rise and fall of Earth's oceans, the phenomenon we call tides. Tides are born from tidal forces, the gravitational interplay between the Earth, Moon, and Sun. While the Moon is the dominant force behind these colossal movements of water, the Sun contributes 40% of the Moon's pull, enhancing and modulating the ebb and flow. The interplay of these two gravitational giants gives rise to patterns we recognize as spring tides and neap tides, complex rhythms that govern coastal waters across the globe. Tides manifest as two enormous bulges of water in Earth's oceans. One bulge forms on the side of the planet facing the Moon, drawn by the satellite's gravitational attraction. A corresponding bulge emerges on the opposite side, a product of either centrifugal forces created by the Earth-Moon system or the subtle differential in gravity between the Earth and the distant ocean water. As Earth rotates beneath these shifting bulges, the oceans rise and fall in a nearly perpetual dance, producing 2 high tides and 2 low tides roughly every 24 hours. Yet, the precise timing of these tides is slightly longer than 12 hours, extended by about 25 minutes due to the moon's gradual motion in the direction of Earth's rotation. If Earth were a perfect sphere of water, free from continents and friction, tides would be simple and predictable, rising and falling by roughly 1 meter. Reality, however, is far more intricate. The friction of water against the ocean floor slows the flow, while the inertia of moving water allows it to continue even after the moon's pull has shifted. Shallow ocean basins near continents act like channels, forcing water to slosh back and forth, creating complex local patterns. Because of these dynamics, the exact times and heights of tides are best observed rather than calculated, a reminder of the ocean's ever-changing nature. Yet tides do more than shape coastlines. They gradually siphon Earth's rotational energy, slowing our planet's spin through a subtle frictional resistance. This energy doesn't vanish. It transfers to the moon, nudging it into a higher orbit and causing it to move ever so slightly more slowly around the Earth, a process known as tidal acceleration. Over time, this ongoing exchange increases the distance between Earth and Moon, while our days grow imperceptibly longer. Precision measurements using mirrors left by Apollo astronauts reveal the moon is drifting away at a rate of approximately 38 millimeters per year, roughly the pace at which fingernails grow. Meanwhile, atomic clocks, precise to fractions of a second, confirm that each year Earth's days lengthen by about 17 microseconds, necessitating the occasional addition of leap seconds to maintain our timekeeping. Far into the future, this celestial choreography could lead to complete synchronization between Earth and Moon, a state known as tidal locking. Already, we observe the moon displaying only one face toward Earth, the near side, while the far side remains hidden from view. Hypothetically, if Earth survives billions of years more, tidal locking could extend to our planet, creating a mutual gravitational stare between Earth and Moon. However, the Sun, destined to swell into a red giant long before that time, will likely engulf both worlds, making such a scenario a theoretical curiosity rather than a reality. The Moon's orbit and apparent size also fluctuate. Its distance from Earth ranges from about 356,400 kilometers at its closest point, called perigee, to roughly 467,000 kilometers at its farthest, called apogee. This variation makes the moon appear slightly larger or smaller in the sky by up to 14%, which is why solar eclipses can occasionally align so perfectly. The moon's height in the sky shifts with the seasons and the observer's latitude. During winter, the full moon rises higher in the sky than in summer, while at the poles it can linger above the horizon for weeks, casting light during the long polar nights. Tiny organisms, such as Arctic plankton, even rely on this lunar illumination to survive months of darkness. From Earth, the moon's appearance changes depending on where one stands. Observers in the northern hemisphere perceive it differently from those in the southern, while in tropical regions, a crescent moon sometimes forms a smiling wet moon, its horns pointing upward. Its phases, from new to full, reveal a constant dance between sunlight, shadow, and our vantage point. The moon, slightly tilted by just over half a degree relative to Earth's orbital plane, undergoes subtle seasonal shifts, with its poles experiencing alternating periods of sunlight and darkness over a draconic year of roughly 347 days. The moon's near side, eternally facing Earth, is complemented by its far side, equally sunlit but hidden from view. The tidally locked rotation we see today was not always the moon's fate. Early in its history, the moon spun more rapidly until the relentless tug of Earth's gravity and resulting internal friction gradually slowed its rotation. Energy lost in this process transformed into heat until the moon's spin synchronized perfectly with its orbit, creating the enduring familiar visage we observe tonight. Modern exploration continues to reveal lunar secrets. NASA's Lunar Prospector mission in 1998 and 1999 mapped hydrogen-rich regions, indicating the presence of ancient ice deposits at 2 locations on opposite sides of the moon. These may correspond to ancient lunar poles before tidal locking altered its rotation. Even the interplay of sunlight and earthlight contributes to the moon's visual charm. Reflected sunlight from Earth softly illuminates the moon's shadowed portions, producing a delicate glow observable from our planet. In essence, the moon is a dynamic, living world of its own, shaping tides, subtly altering Earth's rotation, hosting lingering quakes, and preserving the record of ancient water in its frozen craters. Every observation, every measurement reveals a complex interplay of forces, a narrative of celestial physics that binds Earth and Moon in a slow, inexorable dance across billions of years. Its presence in the night sky is more than romantic. It is a chronicle of gravity, motion, and time, a testament to the intricate mechanics of our cosmic neighborhood. However, near the Moon's equator, the dramatic shifts we call seasons barely register. Unlike Earth, where the tilt of the axis drives the changing patterns of weather and sunlight, the Moon's equatorial regions experience little variation in temperature over the course of its long month. As the Moon steadily circles our planet, the interplay of sunlight and shadow paints the familiar tapestry of lunar phases that has captivated humanity for millennia. From the delicate crescent to the resolute half-moon, the rounded gibbous, and the resplendent full moon, these transformations arise simply from the angle at which sunlight illuminates the moon and how much of that illuminated surface is visible from Earth. Each phase is a celestial performance, choreographed by the positions of the sun, the moon, and our vantage point on the planet below. The moon's brightness and apparent size are far from constant. Its orbit is not a perfect circle, but an elongated ellipse, which brings it closer to Earth at times, a point called perigee, and farther away at apogee. When the moon reaches perigee, it can appear up to 30% larger and noticeably brighter than at apogee. If a full or new moon coincides with this near approach, we witness what astronomers and sky watchers call a supermoon, a lunar spectacle that seems unusually grand in the night sky. For centuries, people have speculated that the moon's surface changes over time, observing apparent shifts or anomalies with limited instruments and often over-interpreting blurred or fleeting glimpses. Modern science, with its advanced telescopes and lunar missions, has largely demystified these claims. Yet, subtle phenomena like outgassing, tiny bursts of gas escaping from beneath the lunar surface, still occur occasionally and may account for some of the strange observations of the past. Remarkably, scientists have identified one region roughly 2 miles across that appears to have been altered by such a gas release approximately 1 million years ago, leaving a subtle but lasting imprint on the lunar landscape. Though the moon reflects only a modest amount of sunlight, its surface slightly more reflective than weathered asphalt, it shines as the second brightest object in our sky, surpassed only by the sun. This brilliance is intensified by the opposition surge, a sudden increase in apparent brightness when the moon is directly opposite the sun relative to our line of sight. At a quarter moon, the lunar glow seems a mere tenth of the full moon's radiance, far dimmer than one might intuitively assume. Our perception also plays tricks. Against the deep darkness of night, the moon appears even brighter to human eyes than its actual luminance. The lunar soil reflects light in a distinctive way, sending it back toward its source, which is why the edges of a full moon can seem just as luminous as its center. The true color of the moon is a subtle brownish gray, yet it can appear dramatically different under varying conditions. During a lunar eclipse, sunlight filtered through Earth's atmosphere bathes the moon in a deep red glow, earning the poetic title blood moon. When the moon hovers low on the horizon, the same atmospheric scattering can tint it reddish as well. In rarer instances, particles from volcanic eruptions or massive wildfires can scatter light to produce an eerie bluish hue, a phenomenon sometimes called a blue moon. Curiously, these terms, blood moon and blue moon, also refer to special calendrical events, not solely color changes. Eclipses themselves are the result of near-perfect cosmic alignments, a phenomenon known as syzygy. Solar eclipses occur at the new moon when the moon positions itself directly between Earth and the sun, while lunar eclipses take place during a full moon when Earth blocks sunlight from reaching the lunar surface. Astonishingly, the sun is about 400 times wider than the moon, yet it is also roughly 400 times farther from Earth, making them appear nearly identical in size to human eyes. Minute variations in their distances give rise to different eclipse types: total solar eclipses, where the moon completely obscures the sun, and annular eclipses, where a ring of sunlight encircles the lunar silhouette. During totality, the sun's radiant outer atmosphere, the corona, emerges, casting a surreal ethereal glow across the sky. Over vast stretches of time, the moon is gradually drifting away from Earth. Its increasing distance will eventually render total solar eclipses impossible, as the moon will appear too small to cover the sun entirely. Simultaneously, the sun is slowly swelling as it ages toward its red giant phase, subtly enlarging in our sky over millions of years. Eons ago, the moon appeared larger than the sun, allowing total eclipses to occur more readily. Looking forward, we can anticipate a distant future when the lunar silhouette will never fully obscure the solar disk again. The moon's orbit is tilted slightly more than 5 degrees relative to Earth's path around the sun, so eclipses are rare rather than regular occurrences. For one to happen, the moon must cross the precise intersection points of its orbital plane with Earth's, known as nodes. These celestial alignments follow a predictable rhythm called the Saros cycle, repeating approximately every 18 years and enabling astronomers to forecast eclipses with remarkable accuracy. Another fascinating lunar phenomenon is occultation, which occurs when the moon passes in front of a star or planet, temporarily obscuring it from view. Every solar eclipse is, in essence, the occultation of the sun itself. Because the moon is relatively close to Earth, these events appear differently depending on the observer's location, and as the moon's orbit slowly shifts, new stars are occulted each year. Human fascination with the moon spans tens of thousands of years. Some of the earliest cave paintings, potentially 40,000 years old, depict bulls and geometric symbols that may have been used to track lunar phases. Ancient tally sticks, dating back 20 to 30,000 years, likely recorded days in relation to the moon's cyclical rhythm. Early civilizations often deified the moon, creating gods and goddesses that represented its influence and incorporated lunar imagery into early writing systems. One of the oldest known depictions, carved into a rock known as Orthostat 47 in Northern Ireland, dates back around 3,000 years before the Common Era. In the 3rd millennium BCE, cultures worshipped the crescent moon, often associated with the lunar deity Nana, also known as Sin, intertwining the celestial rhythms of the night sky with the spiritual and cultural life of humanity. One of the most extraordinary figures of ancient Mesopotamia was Enheduanna, a woman whose name still resonates through the corridors of history. She was not only a high priestess, but also a poet of remarkable skill, and she happened to be the daughter of Sargon the Great, a king whose influence shaped an entire era. Enheduanna lived roughly 2,334 to 2,279 years before the Common Era, a period when the heavens were both a source of wonder and a guide for human activity. Within the sanctified walls of her temple, she meticulously observed the moon, charting its path across the sky with care and precision, demonstrating an early disciplined approach to astronomy long before telescopes existed. Thousands of years later, around 1800 to 1600 years before the Common Era, a fascinating artifact appeared far from Mesopotamia in what is now Germany, the Nebra sky disk. This circular piece of bronze inlaid with gold captured the night sky in astonishing detail, depicting stars alongside the moon, including the Pleiades cluster. Scholars consider this disk the oldest known representation of the moon in relation to other celestial bodies, a testament to humanity's enduring fascination with the cosmos. By the 5th and 4th centuries before the Common Era, intellectual curiosity about the moon had spread widely. The Greek philosopher Anaxagoras, for instance, proposed that both the sun and the moon were enormous rocky spheres, with the moon simply reflecting the sun's light, a remarkable insight that foreshadowed modern understanding. Meanwhile, in Mesopotamia, Babylonian astronomers had already deciphered the 18-year Saros cycle of lunar eclipses, while Indian scholars tracked the moon's monthly shifts across the sky. Across Asia, Chinese astronomer Shi Shen compiled detailed instructions for predicting both solar and lunar eclipses, demonstrating a sophisticated grasp of celestial mechanics. The Greek philosopher Aristotle, who lived from 384 to 322 years before the Common Era, contemplated the moon's role as the boundary between the ever-changing earthly realm and the immutable heavens, ideas that would shape centuries of philosophical and scientific thought. Around the same time, Archimedes, a mathematical genius born in 287 years before the Common Era, engineered a remarkable device, an early planetarium, that simulated the motions of the moon and other celestial bodies, blending theoretical insight with mechanical innovation. Meanwhile, Greek thinkers like Seleucus made strides in understanding Earth's oceans, recognizing that the moon's gravitational pull caused tides, with their rise and fall determined by the moon's position relative to the sun. Aristarchus, another brilliant mind, made one of the earliest estimates of the moon's distance, proposing it lay about 20 times the radius of Earth from our planet, a bold approximation that revealed the ingenuity of ancient astronomers. In China, during the Han Dynasty, scholars believed the moon consisted of a unique form of energy called qi, yet they also understood that its glow was sunlight reflected. The scholar Jing Fang, living from 78 to 37 years before the Common Era, correctly described the moon as spherical, a conclusion confirmed centuries later by astronomers like Ptolemy, who lived from 90 to 168 years in the Common Era. Ptolemy calculated that the moon was roughly 59 times Earth's radius away, with a diameter slightly more than 1/4 that of Earth, a surprisingly accurate estimate for antiquity. Around the 2nd century of the Common Era, the imagination of writers like Lucian gave birth to early science fiction, recounting journeys to the moon and encounters with its inhabitants, blending scientific curiosity with the human desire for storytelling. In the year 510 of the Common Era, the Indian astronomer Aryabhata reaffirmed that the moon shines by reflecting sunlight, a principle that would be refined by later scholars. The Islamic polymath Ibn al-Haytham, living from 965 to 1039, corrected a common misconception, demonstrating that the moon's surface emits light diffusely in all directions, rather than acting like a mirror. During China's Song Dynasty, the polymath Shen Kuo, who lived from 131 to 195, offered an imaginative analogy for the moon's phases. He likened it to a round silver ball dusted with white powder, appearing crescent-shaped when viewed from the side, mimicking the lunar phases observed in the sky. By the Middle Ages, most people had come to accept the moon as a spherical object, though many still imagined its surface as perfectly smooth. This perception changed dramatically in 1609, when Galileo Galilei used one of the earliest telescopes to examine the moon closely. In his groundbreaking work, Sidereus Nuncius, he presented detailed drawings showing mountains, craters, and other irregularities, shattering centuries of idealized assumptions. Curiously, another observer, Thomas Harriot, had produced similar lunar sketches months earlier, but they remained unpublished, leaving Galileo's work as the more influential record. The invention of the telescope sparked an era of lunar cartography. By the late 17th century, scientists embarked on detailed mapping of the moon, naming its features and categorizing its craters and plains. Italian astronomers Giovanni Battista Riccioli and Francesco Maria Grimaldi were instrumental in this effort, devising a nomenclature system that remains in use to this day, linking the past to the present through a shared language of discovery. Through centuries of observation, imagination, and mechanical ingenuity, humanity slowly peeled back the mysteries of the moon, transforming it from a distant, enigmatic light in the sky into a celestial neighbor whose features, movements, and influence could be systematically understood. From Enheduanna's temple to Galileo's telescope, the story of our relationship with the moon is a testament to curiosity, intellect, and the relentless human drive to know the cosmos. In the early decades of the 19th century, precisely between the years 1834 and 1836, two German astronomers, Wilhelm Bayer and Johann Hinrich von Medler, embarked on an ambitious project to chart the moon with a precision never before attempted. Their painstaking observations culminated in a detailed lunar map known as the Mappa Selenographica. By 1837, they had published a groundbreaking book titled Der Mann the Moon, which represented the very first systematic attempt to study the moon using measurements akin to those used in terrestrial cartography. Their meticulous work went beyond mere observation. It included the heights of over 1,000 lunar mountains, providing an unprecedented level of accuracy that transformed lunar science from a field of speculation into one grounded in precise data. Long before Bayer and von Medler, in the early 17th century, Galileo Galilei had peered through his telescope and first noted the presence of craters on the moon's surface. For decades, these formations were assumed by scientists to be volcanic in origin. However, in the 1870s, the astronomer Richard Proctor proposed a radically different explanation, that the craters were not born from fire and molten rock, but from celestial collisions, objects striking the moon with tremendous force. Proctor's ideas gained empirical support by 1892, when the geologist Grove Carl Gilbert conducted experiments that confirmed the plausibility of impact craters. Over the following decades, from the 1920s through the 1940s, comparative studies of Earth's landscapes and lunar topography further validated the theory. These insights laid the foundation for a new scientific discipline known as lunar stratigraphy, dedicated to understanding the layered history and evolution of the moon. By the 1950s, this field had expanded rapidly and evolved into what became known as astrogeology, a burgeoning branch of science devoted to studying the geological characteristics of celestial bodies. The end of the Second World War brought technological innovations that would change humanity's relationship with space. Advances in rocketry, initially driven by military research, soon enabled the construction of powerful rockets capable of escaping Earth's gravitational pull. By the late 1950s, both the Soviet Union and the United States had developed rockets strong enough to send spacecraft into orbit and beyond, igniting what would famously become the space race, a fierce competition to claim dominance in space exploration. A significant focus of this race was the moon, humanity's nearest celestial neighbor. In 1957, during the International Geophysical Year, the Soviet Union launched Sputnik 1, the first human-made object to orbit Earth, signaling the beginning of a new era. This was quickly followed by the Soviet lunar program. After 3 initial setbacks in 1958, Soviet engineers achieved success in 1959. Luna 1 became the first spacecraft to escape Earth's gravitational hold and pass close to the moon. Soon after, Luna 2 deliberately impacted the lunar surface, marking the first human-made object to touch the moon. By the end of that landmark year, Luna 3 had navigated the far side of the moon, the hemisphere forever hidden from Earth, and returned the first images of its mysterious terrain. The mid-60s brought further monumental achievements. In 1966, Luna 9 achieved the first soft landing on the moon, while Luna 10 became the first spacecraft to orbit it. Meanwhile, in the United States, President John F. Kennedy had, in 1961, set a bold national goal to land a human on the moon before the decade's end. NASA responded with a series of uncrewed missions to study the lunar surface, including the Ranger, Lunar Orbiter, and Surveyor programs. These missions were critical for determining suitable landing sites and understanding the moon's surface conditions. In parallel, the Apollo program began preparing for human spaceflight. After rigorous testing, both with and without astronauts, Apollo 8 made history in 1968 as the first human mission to orbit the moon. Interestingly, just 3 months earlier, 2 tortoises had orbited the moon aboard the Soviet Zond 5 spacecraft, becoming the first Earth creatures to complete a lunar journey, followed by additional turtles on Zond 6. Then came humanity's moment of triumph. On the 21st of July, 1969, at precisely 2:56 Universal Time, American astronaut Neil Armstrong stepped onto the moon's surface, becoming the first human ever to do so. As commander of NASA's Apollo 11 mission, Armstrong's footsteps marked the pinnacle of the space race, witnessed live by an estimated 500 million people worldwide, an audience unprecedented in human history. Remarkably, at the same time, the Soviet spacecraft Luna 15 was orbiting the moon, marking the first occasion in history when 2 separate missions explored the moon simultaneously. Between Apollo 11 and Apollo 17, excluding Apollo 13, which had to abort its mission due to an onboard emergency, astronauts returned to Earth with a total of 380 kilograms, or 838 pounds, of lunar rocks and soil. These were collected in 2,196 distinct samples. During each mission, scientific instruments were deployed on the moon's surface, including seismometers to measure moonquakes, heat flow sensors, and magnetometers to record magnetic fields. These instruments were installed across the Apollo 12, Apollo 14, Apollo 15, Apollo 16, and Apollo 17 missions. Although live data transmission from many of these instruments ceased in late 1977 due to budgetary constraints, some continue to function today. Notably, retroreflectors, special mirrors designed to reflect laser beams from Earth, still enable precise measurements of the distance between the Earth and the Moon, connecting humanity to our celestial neighbor in real time more than half a century after the first footprints were made. And so, these carefully positioned mirrors on the lunar surface perform a role that might seem almost magical at first glance. They capture and reflect powerful laser beams sent across the vast void from Earth, bouncing them back with astonishing precision. This simple yet elegant interaction allows scientists to calculate the distance between our planet and its lone satellite with extraordinary accuracy, down to mere centimeters, offering a window into the subtle gravitational dance between Earth and the Moon that has persisted for billions of years. The last manned mission of the Apollo era, Apollo 17, concluded in 1972, marking the end of an extraordinary chapter of human exploration. Only a year later, in 1973, the United States launched Explorer 49, the final American spacecraft focused exclusively on lunar study until the resurgence of interest decades later. While the US turned its gaze elsewhere, the Soviet Union remained deeply committed to robotic lunar exploration. In 1970, they sent Luna 17, which deployed Lunokhod 1, the first remotely controlled rover ever to traverse the surface of another world. This pioneering machine crept across the moon's desolate landscape, sending back images and data that ignited imaginations worldwide. Between 1970 and 1976, 3 more Soviet missions, Luna 16, Luna 20, and Luna 24, brought back a cumulative total of roughly 300 grams of lunar soil and rock, precious samples that would fuel scientific study for decades. Yet after Luna 24 in 1976, the fervor surrounding lunar exploration waned. For the following 14 years, space programs turned their attention toward other planets, including Venus and the outer reaches of the solar system. Landmark missions, such as Pioneer 10 in 1972, expanded our understanding of Jupiter and the cosmic neighborhood, while satellites dedicated to observing Earth from orbit became increasingly sophisticated. The LANCAT program, inaugurated in 1972, exemplified this new focus, alongside the development of the Salyut series of space stations beginning in 1971, which demonstrated humanity's growing ambition to live and work in orbit. Amid this shift, the only significant lunar milestone was the negotiation of the Moon Treaty in 1979, officially ratified in 1984, a document aimed at governing the peaceful use and protection of lunar resources. Yet it would take until 1990 for a new lunar mission to reignite global attention. That year, Japan achieved a historic milestone by sending the Hiten and Hagoromo spacecraft, marking the first time a country outside of the US and the Soviet Union reached the moon. The US returned in 1994 with the Clementine mission, its first lunar expedition since 1973. This robotic probe transformed our understanding of the moon by mapping its entire surface with unprecedented detail, creating 3-dimensional topographical maps and capturing images in multiple wavelengths of light that revealed subtle variations in mineral composition. Just 4 years later, in 1998, the Lunar Prospector mission detected higher concentrations of hydrogen at the moon's poles, hinting at hidden reservoirs of water ice within perpetually shadowed craters, a discovery with profound implications for future lunar habitation. As the new millennium unfolded, a growing number of nations joined the lunar exploration effort. Between 2004 and 2006, the European Space Agency launched its first lunar probe, SMART-1. delivering detailed chemical maps of the moon's surface. China entered the arena in 2007 with Chang'e 1, which orbited the moon for 2 years, producing comprehensive surface imagery. India followed in 2008, sending Chandrayaan-1 and an impact probe to the lunar surface, confirming the presence of water molecules in the lunar soil and mapping its minerals and geological features. June 18, 2009, saw a flurry of American activity as NASA launched the Lunar Reconnaissance Orbiter, LRO, alongside the L-Cross impactor. By October 9th, L-Cross collided with the Cabeus crater, sending plumes of lunar material skyward for analysis, while the LRO remains in orbit, continuously returning high-resolution images and precise measurements of the moon's topography. China's lunar ambitions accelerated in 2010 with Chang'e 2 providing even more detailed mapping over 8 months. By 2013, Chang'e 3 achieved a soft landing with a rover named U2, or Jade Rabbit, the first rover to explore the moon in 40 years. This mission marked China as the third nation to land softly on the lunar surface. In 2014, private enterprise joined the exploration frontier when the Manfred Memorial Moon mission became the first privately funded probe to reach the moon. China's Chang'e 4 made history in early 2019 by landing on the moon's far side, a feat no other nation had accomplished. That same year, India launched Chandrayaan-2, and in 2020, China's Chang'e 5 returned 1,731 grams of lunar rock and soil to Earth, a remarkable achievement that marked humanity's most recent retrieval of lunar material. Meanwhile, the Artemis program, initiated by the United States in 2004, matured into an ambitious vision for a sustainable human presence on the moon. The Artemis Accords, established in 2020, laid the framework for cooperative international exploration, echoing earlier concepts such as the Moon Treaty and ESA's proposals for a lunar village. South Korea launched its first lunar mission, Danuri, in 2022, and by 2024, India and Japan had achieved successful soft landings. Japan's Smart Lander survived 3 frigid lunar nights, demonstrating technological resilience, while IM-1 became the first private company lander to reach the moon. The race intensified with China's Chang'e 6 returning new samples from the far side, and the deployment of multiple robotic rovers using advanced infrared and imaging systems. Pakistan entered the field with its small lunar orbiter, iCube, while commercial missions like Nova C2, ICE Space Lander, and Blue Ghost highlighted the increasingly crowded lunar environment. As the Artemis program and NASA's commercial lunar payload services expand, plans are underway to land astronauts, including the first woman, the first person of color, and the first non-American on the lunar surface during the 2020s. Simultaneously, China continues its Chang'e program and seeks collaboration with Russia, whose lunar ambitions are being revived. By the 2030s, both programs aim to establish permanent lunar bases, supported by orbiting stations like the Lunar Gateway and sophisticated human landing systems. Unlike the Apollo missions, which were brief exercises in exploration, these new efforts emphasize long-term habitation, communication infrastructure, and resource utilization. The U.S. Defense Agency, DARPA, has proposed a decade-long strategy to create the foundations of a lunar economy. Scientists and ethicists alike are increasingly attentive to preserving the moon's fragile environment from dust, debris, and human-made radio interference. Experts such as Alice Gorman argue that though lifeless at first glance, the moon should be treated as a partner in humanity's journey into space, not merely a barren rock. Incidents such as the 2019 crash of the Israeli Bereshit lander, carrying resilient tardigrades, underscore the absence of global regulations to prevent biological contamination. Meanwhile, the growing accumulation of debris in lunar orbit threatens future missions, making waste management an urgent challenge. From this quiet sentinel orbiting Earth, our gaze naturally extends outward to Mars, the fourth planet from the Sun. Its striking reddish-orange hue, the result of iron oxide dust coating its surface, has long earned it the moniker Red Planet. Visible even to the naked eye, Mars's rocky terrain and stark geological features have captivated observers for centuries, inviting generations of humans to wonder, imagine, and one day reach beyond our familiar home. The story of lunar exploration, with its intricate dance of nations, robots, and visionaries, is far from complete. It is a narrative of ambition, ingenuity, and the enduring human desire to reach for the stars, a journey that now stretches from the moon's cratered plains to the dusty red deserts of Mars, marking the next frontier in our eternal quest to understand the cosmos. In fact, Mars holds the distinction of being the second smallest planet in our solar system, a compact world with a diameter of roughly 6,779 kilometers, which translates to around 4,212 miles. A single day on Mars, known as a sol, stretches for about 24 and a half hours, remarkably close to the length of a day on Earth, creating a familiar rhythm for any future Martian visitor. Yet a year on Mars unfolds on a much grander timescale. The planet takes nearly 687 Earth days to complete a full orbit around the Sun, almost 1.9 Earth years, meaning that Martian calendars move far more slowly than our own. Mars is accompanied by two tiny moons, Phobos and Deimos, whose appearances defy the conventional expectation of a smooth, round satellite. Instead, these moons are irregularly shaped, resembling enormous rocky potatoes adrift in the void. Their unusual forms hint at a violent past, likely shaped by cosmic collisions that prevented them from ever forming perfect spheres. The Martian surface itself is a study in dramatic contrasts. The northern hemisphere is remarkably flat and smooth, almost eerily so, while the southern hemisphere is scarred with craters and rugged highlands. This striking division is known as the Martian dichotomy and remains one of the most intriguing geological features in the solar system. Adding to the planet's visual majesty are colossal natural structures. Towering above the landscape is Olympus Mons, an extinct volcano soaring 21.9 kilometers, or around 13.6 miles high, making it the tallest volcano ever discovered across all planets. Equally impressive is the canyon system known as Valles Marineris, stretching nearly 4,000 kilometers or 2,500 miles, carving a gash across the planet that dwarfs any canyon on Earth. Despite appearances, Mars is far from a dead world. Seismic activity has been detected beneath its surface, hinting at hidden geologic energy still at work. Dust devils whirl across the terrain, tracing invisible patterns, while delicate wisps of cirrus clouds drift in the thin atmosphere. The polar ice caps, rich in frozen carbon dioxide, expand and contract with the seasons, contributing to a climate of extreme variability. Temperatures can plunge to as low as minus 78.5 degrees Celsius, roughly minus 109.3 degrees Fahrenheit. And yet, on rare warm days, they can rise to around 5.7 degrees Celsius, or 42.3 degrees Fahrenheit. Seasons on Mars occur thanks to its tilted axis, a slight 25-degree slant compared with Earth's 23.5 degrees. This tilt ensures that, just as on Earth, different regions experience shifts in sunlight and temperature, giving the planet a dynamic, changing face over the course of its orbit. Mars's history stretches back some 4.5 billion years. During its earliest era, the Noachian period, from roughly 4.5 to 3.5 billion years ago, the planet endured relentless bombardment by space rocks. These collisions carved deep valleys and river channels, and some scientists hypothesize that oceans may once have graced the Martian surface. Following this came the Hesperian period, spanning from about 3.5 to between 3.3 and 2.9 billion years ago, when massive volcanic eruptions and cataclysmic floods reshaped the landscape, carving immense channels and plains. The most recent phase, the Amazonian period, continues to the present day. Here, wind has become the dominant sculptor of the planet, shaping dunes and dust-covered plains with relentless, slow artistry. Because of its long and turbulent history, Mars has captivated scientists with questions about life, whether it may have once harbored living organisms or still possesses the potential to do so. The modern era of exploration began in the mid-20th century, when robotic spacecraft first ventured toward the Red Planet. Mariner 4 approached closely in 1965, while Mars 2 became the first to achieve orbit in 1971. The milestone of a successful landing came 5 years later with Viking 1 in 1976. By 2023, at least 11 active spacecraft were either orbiting or traversing Mars' surface, gathering an astonishing wealth of data and continuously reshaping our understanding of this enigmatic world. Mars is widely regarded as the prime candidate for human exploration in the future. Although no crewed missions have been scheduled for the 2020s, scientists and engineers worldwide are tirelessly developing the technologies that will one day enable humanity to set foot on its surface. The planet itself emerged from the primordial dust and rocks swirling around the young sun. During a tumultuous process known as runaway accretion, Mars gradually gathered enough material to coalesce into a fully formed planet. Its position in the solar system endowed it with a distinctive chemical signature. Elements that turn into gases at relatively low temperatures, such as chlorine, phosphorus, and sulfur, are more abundant on Mars than on Earth. Researchers believe that the sun's intense early solar wind may have driven these lighter elements outward, where they became incorporated into the nascent planet. After planetary formation, the inner solar system experienced a violent phase called the Late Heavy Bombardment, when massive objects rained down on planets and moons alike. Around 60% of Mars's surface still bears scars from these ancient impacts, including colossal basins formed by strikes from enormous celestial bodies. Every crater, every ridge, and every basin tells a story, a silent testament to billions of years of cosmic upheaval that shaped Mars into the intricate, awe-inspiring world we observe today. However, in recent years, a growing number of planetary scientists have begun to challenge long-held assumptions about the Late Heavy Bombardment, a period once thought to have universally shaped the inner planets with a relentless rain of asteroids. The narrative of Mars, in particular, is shifting as new evidence emerges that paints a picture far more dramatic than previously imagined. Buried beneath the planet's northern hemisphere is a colossal structure, a crater of mind-boggling scale, stretching approximately 10,600 kilometers from end to end and spanning 8,500 kilometers across. To put this in perspective, it is roughly 4 times larger than the immense South Pole Aitken Basin on the Moon, the largest impact basin previously known in our solar system. Should these findings be confirmed, this feature would not only redefine Mars's geological history, but also claim the title of the largest impact basin ever discovered. Researchers propose that this gargantuan depression was formed when a planetary-sized object, potentially as large as Pluto, collided with Mars roughly 4 billion years ago. The consequences of such an impact would have been catastrophic, reshaping the planet's crust, generating the smoother northern plains, and creating the stark geological contrast between the northern lowlands and southern highlands that remains evident today. This monumental collision may have set the stage for much of what we now observe on the Red Planet, a dramatic reminder that Mars's past is far from static. Adding another twist to Mars's history, a groundbreaking study from the year 2023 suggests that the planet may once have had a ring system reminiscent of Saturn's. By meticulously analyzing the orbit of Deimos, one of Mars's diminutive moons, scientists have inferred that billions of years ago, somewhere between 3.5 to 4 billion years in the past, Mars hosted a much larger moon, potentially 20 times the mass of Phobos. This primordial satellite may have eventually broken apart, forming a spectacular ring system, leaving Phobos as the final remnant of its once massive companion. Mars's geological record is organized into 3 primary time periods, each marking dramatic shifts in the planet's surface and interior activity: the Noachian, Hesperian, and Amazonian periods. The Noachian period, dating from roughly 4.5 billion to 3.5 billion years ago, represents the dawn of Martian history. It was during this epoch that the planet's oldest surface features, including vast impact craters and immense volcanic formations, first took shape. One prominent feature, the Tharsis Bulge, towers above the surrounding landscape, a testimony to the planet's early volcanic vigor. Toward the close of this era, colossal floods of water carved deep valleys and channels across the terrain, evidence that liquid water once flowed abundantly across the Martian surface. This period draws its name from Noachis Terra, a region characterized by rugged, ancient landscapes scarred by asteroid impacts. Following this, the Hesperian period unfolded, lasting from around 3.5 billion to between 3.3 and 2.9 billion years ago. During this time, extensive lava flows spread across the planet, creating vast plains of solidified rock and underscoring Mars's continued internal dynamism. This era, named after Hesperia Planum in the planet's southern hemisphere, reflects a time when volcanic activity dominated, reshaping the surface on a massive scale. The Amazonian period, beginning between 3.3 and 2.9 billion years ago and continuing to the present day, marks Mars's most recent geological chapter. Fewer impact craters on surfaces from this period suggest that the planet experienced a quieter epoch in terms of external bombardment. Yet Mars was far from dormant. Olympus Mons, the tallest volcano in the solar system, rose during this era along with other extensive lava flows. Even within the last 200 million years, volcanic activity has continued, with regions such as Elysium Planitia bearing witness to massive lava deposits. Some areas, like Cerberus Fossae, show evidence of water flowing through fissures less than 20 million years ago, an astonishingly recent event in planetary terms. Observations from orbiters like the Mars Reconnaissance Orbiter have even captured avalanches, providing tangible proof that the planet's surface is still shaped by dynamic forces. Mars is roughly half the diameter of Earth, with a surface area slightly smaller than all of Earth's continents combined. It is less dense than our planet, holding about 15% of Earth's volume and only 11% of its mass, which results in surface gravity approximately 38% that of Earth's. The red planet's desert-like appearance, characterized by rocky and dusty terrain, is a consequence of widespread iron oxide that gives its distinctive reddish-orange hue. Yet Mars is not a monotone world. Its soil can appear golden, brown, tan, greenish, or even butterscotch depending on mineral composition and lighting. Structurally, Mars mirrors Earth in its layered composition. Its crust, a rocky outer shell, ranges in thickness from as thin as 6 kilometers in regions like Elysium Planitia to as thick as 117 kilometers in the southern highlands, averaging between 42 and 56 kilometers overall. In comparison, Earth's crust averages roughly 27 kilometers. Rich in silicon, oxygen, iron, magnesium, aluminum, calcium, and potassium, the Martian crust supports a seismically active interior. NASA's InSight lander recorded over 450 quakes in 2019, highlighting ongoing tectonic activity. Beneath the crust lies a silicate mantle, responsible for much of Mars's volcanic landscape. Its upper regions exhibit a low-velocity zone where seismic waves slow, extending to around 250 kilometers in depth. Unlike Earth, Mars lacks a thick insulating mantle layer. Beyond roughly 150 kilometers, the mantle transitions into a structure similar to Earth's transition zone. At the base, a layer of molten silicate rock, approximately 150 to 180 kilometers thick, separates the mantle from the planet's core. Mars's core, composed primarily of iron and nickel along with lighter elements like sulfur, oxygen, carbon, and hydrogen, is fully molten, unlike Earth's solid inner core. It occupies about half the planet's radius, roughly 1,650 to 1,675 kilometers, and maintains temperatures between 2,000 and 2,400 Kelvin, far cooler than Earth's core, which reaches 6,200 Kelvin. The Martian surface is predominantly covered with a volcanic rock called tholeiitic basalt, while other regions exhibit higher silica content resembling andesitic rocks or even silica glass. Mineral diversity is significant. Plagioclase clays and feldspar appear in darker zones, sheet silicates and silicon-rich glass are present in northern areas, and calcium-rich pyroxenes are concentrated in the southern highlands. Hematite and olivine emerge in specific locales, while a fine coating of iron oxide dust blankets much of the planet, creating its signature coloration. When NASA's Phoenix lander analyzed Martian soil, it revealed slightly alkaline properties with a pH of roughly 7.7 and an abundance of essential nutrients such as magnesium, sodium, potassium, and chlorine, the same elements that nourish plants on Earth, hinting at a past where life might have found the raw ingredients for growth. Mars's story, from its titanic collisions and volcanic upheavals to its icy plains and whispering dust storms, unfolds like a planetary saga. Every ridge, crater, and valley is a page in a history of both violence and transformation, a testament to a world that, while quieter than its fiery past, continues to evolve and surprise us even today. However, the story of Mars is not just written in its striking red dust or dramatic landscapes. It is also hidden in the subtle chemistry of its soil. Beneath its rusty surface lies approximately 0.6% of perchlorate, a chemical compound toxic to humans that complicates any potential exploration or colonization. This chemical hazard is just one part of the complex environmental tapestry that defines the Martian surface, a world where dark streaks trace the planet's steep slopes with an almost deliberate elegance. These streaks, sudden, ephemeral, and mysterious, often appear around craters, troughs, and valleys, stretching hundreds of meters, their darkness gradually fading with time. They weave around boulders and natural obstacles, hinting at forces that sculpt the landscape in ways that are still the subject of intense scientific inquiry. Some experts suggest these streaks expose darker soil beneath lighter dust layers that have slipped away, while others theorize that they may be shaped by the invisible hand of dust devils, transient water flows, or perhaps even microbial activity. Each hypothesis reflects the profound mystery Mars holds, a puzzle that scientists are meticulously piecing together with every observation and mission. Radiation is another invisible adversary for future explorers. On the Martian surface, the average daily radiation reaches approximately 64 millisieverts, a number that, while lower than the 1.84 millisieverts astronauts encountered during the voyage to and from Mars, is still far above the roughly 0.5 millisieverts experienced daily aboard orbiting space stations. Certain regions offer relative refuge. Hellas Planitia, for example, sees radiation levels dip to around 0.342 millisieverts per day, while lava tubes near Hadrias Mons could shield explorers to levels as low as 0.64 millisieverts per day, comparable to long-haul airline flights on Earth. Mars today lacks a strong global magnetic field, but the rocks whisper secrets of a bygone era. Scientists have uncovered magnetic patterns locked within the Martian crust, evidence suggesting that long ago, Mars might have hosted a magnetic field that flipped periodically, much like Earth's. These fossilized magnetic stripes, reminiscent of the oceanic crust on Earth, hint at the possibility that Mars once experienced plate tectonics, the slow dance of colossal crustal plates over a molten interior. Research, first sparked in 1989 and expanded with data from the Mars Global Surveyor in 2005, posits that this tectonic activity may have ceased roughly 4 billion years ago when Mars' internal dynamo, the engine that generates a magnetic field, went dormant, allowing the magnetic signals to freeze into the rocks. The fascination with Mars stretches far beyond modern spacecraft. Long before probes and orbiters, two early 19th century astronomers, Jan Heinrich von Medler and Wilhelm Beer, meticulously mapped the red planet. While they are often remembered for their lunar charts, their work on Mars laid a foundation for planetary cartography. They recognized that dark and light areas on Mars were persistent features, not illusions, and they refined the measurement of a Martian day. After a decade of painstaking observation, Medler produced the first detailed map of Mars in 1840, setting the stage for centuries of exploration. Naming Mars features reflects a blend of human culture and scientific curiosity. Albedo features, the lighter and darker regions visible from Earth, often borrow from ancient mythology, while massive craters exceeding 50 kilometers in diameter honor deceased scientists and writers who contributed to Mars's study. Smaller craters carry the names of towns and villages worldwide with populations under 100,000, and the planet's valleys follow a similar pattern. Grand valleys are christened with words meaning Mars or star in various languages, while minor valleys mirror earthly rivers. Some names endure, updated as our knowledge grows. What was once Nix Olympica, the snows of Olympus, is now Olympus Mons, the tallest volcano on Mars. From our terrestrial vantage point, Mars is divided visually into contrasting landscapes. Pale regions, rich in iron-laden dust, were once thought to be continents and were named accordingly, Arabia Terra and Amazon Planitia among them, while darker areas, once imagined as oceans, received names like Mare Erythraeum and Mare Serenum. The largest of these dark expanses, Cerberus Major Planum, is discernible even through modest telescopes. The Martian poles host permanent ice caps, Planum boreum in the north and Planum austral in the south. Mapping Mars required innovation, for the planet has no oceans and thus no natural sea level. A reference point for elevation called the areoid was established at the height where atmospheric pressure is 610. 5 pascals, a delicate balance known as the triple point, where water can simultaneously exist as a solid, liquid, and gas. This minute pressure is merely 0.6 of 1% of Earth's sea level pressure, highlighting the stark differences between the two worlds. Modern cartography divides Mars into 30 quadrangles, each named after classical surface features, facilitating a systematic approach to planetary exploration. Recent mapping endeavors, including work in 2023 with the HOPE spacecraft and NASA imagery, have produced increasingly precise global maps, unveiling details of volcanic landscapes and highland regions like Tharsis. Here lies Olympus Mons, a shield volcano of staggering scale, more than 370 miles wide. From base to summit, it rises over 13 miles, more than twice the height of Mauna Kea, and if measured from surrounding plains, its peak reaches roughly 16 miles above the landscape, nearly 3 times the height of Mount Everest, potentially the tallest mountain in the solar system. Mars' surface is a study in contrasts. The northern hemisphere is smooth, shaped by ancient lava flows, while the southern hemisphere is pockmarked with craters, scars from eons of cosmic bombardment. Around 4 billion years ago, a massive impact may have struck the northern plains, leaving an enormous basin possibly larger than any known impact site in the solar system, encompassing an area comparable to the combined continents of Europe, Asia, and Australia. In total, Mars bears more than 43,000 impact craters measuring at least 5 kilometers across, a testament to the planet's long and violent history. This is a world of extremes, mysteries, and enduring beauty. A planet that, layer by layer, reveals the intricate interplay of chemistry, geology, and cosmic forces, drawing us into an ever-deepening story that is far from complete. And so we begin with Hellas, one of Mars's most awe-inspiring and monumental features. A crater so immense that it seems almost unfathomable. Stretching across a staggering 2,300 kilometers and plunging to depths of 7 kilometers, Hellas is a giant etched into the Martian surface. Its sheer size and reflective brightness make it visible even from Earth with the naked eye, an extraordinary beacon in the vast canvas of space. Yet Hellas is only one among many colossal scars left by cosmic collisions. Nearby, the Arga Basin extends roughly 1,800 kilometers across, while the Isidis Basin spans about 1,500 kilometers, each a testament to the violent history of meteorite bombardment that has shaped the red planet over billions of years. Mars's smaller size and lighter mass might suggest it should be struck less frequently than Earth, having its statistical chance of impact from wandering asteroids and comets. But in reality, Mars lies closer to the bustling asteroid belt, the chaotic region between itself and Jupiter, where debris constantly drifts through the solar system. This proximity means Mars encounters spaceborne objects more often than one might expect. In addition, short-period comets, those that orbit within Jupiter's path, pose a regular threat, adding to the planet's tumultuous history of celestial collisions. Some of these impacts leave more than just scars. Certain craters show evidence of wet ground immediately following an impact, hinting at underground reservoirs of water long buried beneath the Martian surface. No discussion of Mars's surface would be complete without Valles Marineris, a canyon system of epic proportions. Also known historically as Agatha Demon on centuries-old maps imagining Martian canals, this vast trench stretches for roughly 4,000 kilometers, plunging to depths of 7 kilometers in some areas. To contextualize, Valles Marineris is about as long as the entire continent of Europe, spanning a fifth of Mars's circumference. By contrast, Earth's Grand Canyon, iconic as it is, measures a mere 446 kilometers in length and nearly 2 kilometers deep. Scientists theorize that Valles Marineris formed as the surrounding terrain of the Tharsis region swelled, causing the surface to crack and collapse. More recent studies suggest an even more intriguing possibility. The canyon may mark the boundary of 2 enormous blocks of Martian crust sliding past one another, reminiscent of Earth's tectonic plates, hinting at a subtle, ancient form of tectonics on the red planet. Exploration has also revealed mysterious subterranean features. Mars Odyssey, a spacecraft equipped with a thermal camera named Themis, discovered 7 dark openings on the slopes of the massive volcano Arsia Mons. Nicknamed the Seven Sisters in honor of loved ones of the mission scientists, these cavities range in width from roughly 100 to 252 meters, with estimated depths of 73 to 96 meters, though some may descend far deeper. One of these, called Dina, has a clearly visible floor reaching 130 meters. These potential caves could offer vital shelter from Mars's harsh surface conditions, shielding against solar flares, cosmic radiation, micrometeoroids, and ultraviolet light. Mars was not always so exposed. Around 4 billion years ago, the planet had a magnetic field akin to Earth's, a protective barrier that shielded its atmosphere from the relentless solar wind. Catastrophic asteroid impacts and other processes eventually stripped Mars of this shield, leaving its thin atmosphere vulnerable. Today, the solar wind erodes the atmosphere gradually, a process observed by satellites like Mars Global Surveyor and Mars Express, while NASA's MAVEN mission continues to track this ongoing atmospheric loss. The atmosphere that remains is thin beyond comprehension, less than 1% of Earth's sea level pressure. In towering Olympus Mons, pressures drop as low as 30 pascals, whereas in deep valleys like Hellas Planitia, they can reach approximately 1,155 pascals, averaging around 600 pascals. Mars's feeble gravity, about 38% of Earth's, allows the atmosphere to extend much higher than on our home planet. Its scale height, roughly 10.8 kilometers compared to Earth's 6, means air thins more slowly with altitude. Composed predominantly of carbon dioxide at 96%, the atmosphere also contains nearly 2% argon, almost 2% nitrogen, and trace amounts of oxygen and water vapor, all laden with fine dust particles just 1 to 2 micrometers in size. This dust imbues the Martian sky with reddish-brown hues, sometimes even a soft pink glow from iron-rich particles floating in suspension. Among the mysteries of this tenuous air is methane, present in minuscule amounts ranging from about 0.24 parts per billion in the northern winter to 0.65 parts per billion in summer. Methane's fleeting existence, half a year to 4 years, demands an active source. Most scientists attribute it to chemical reactions between water, carbon dioxide, and rocks, especially olivine, though some speculate microbial activity may play a role. Even sound travels differently on Mars. Thin, carbon dioxide-rich air carries vibrations slower and dampens them more quickly than on Earth. Low-frequency sounds drift at roughly 240 meters per second, with higher tones moving closer to 250 meters per second, recorded by NASA's Perseverance rover. Auroras grace Mars too, akin to Earth's northern and southern lights, but they shimmer across the planet rather than clustering at the poles, a direct consequence of Mars's absent global magnetic field. A massive solar storm in September 2017 produced an aurora 25 times brighter than ever before, doubling surface radiation and providing a stark reminder of the planet's vulnerability to cosmic forces. Seasons on Mars mirror those on Earth, but with distinct differences. The planet's elongated orbit causes extreme variations. Perihelion, when Mars is closest to the Sun, triggers southern summer and northern winter, while aphelion, the farthest point, brings southern winter and northern summer. These eccentricities make southern summers scorching, sometimes 30 degrees Celsius warmer than northern ones, and winters far harsher. Equatorial daytime temperatures can reach 35 degrees Celsius, yet nights and polar regions plunge to minus 110 degrees Celsius, a testament to the atmosphere's inability to retain heat. Receiving only 43% of the sunlight Earth does, Mars's environment remains unforgivingly cold. Mars is notorious for colossal dust storms, the largest in the solar system, capable of gusts exceeding 100 kilometers per hour. Sometimes confined, these storms can swell to engulf the entire planet, raising temperatures and shrouding the surface in a hazy red veil. Water persists on Mars, mostly as ice buried beneath layers of dust, particularly at the poles. The southern polar cap alone holds enough frozen water that, if melted, it could blanket Mars to a depth of 11 meters. Liquid water is ephemeral. Only in the lowest, warmest valleys might it survive briefly. Ice crystals form clouds, and occasionally snowfall graces the surface, composed either of frozen water or carbon dioxide, dry ice. The planet's ancient past reveals more watery tales. Around 25 large channels suggest sudden underground outflows that flooded the landscape, while smaller valley networks hint at rainfall in Mars's earliest era. Gullies etched across the southern highlands, facing the equator and situated 30 degrees or more from the poles, provide further evidence of past or possibly ongoing activity. These gullies, young by geological standards, may have been carved by melting ice or other dry processes, their pristine nature indicating they could still be evolving today. Mars, in all its complexity, remains a living record of cosmic violence, planetary evolution, and tantalizing hints of water, perhaps life, and enduring mystery. Its towering canyons, immense craters, shifting dust storms, and elusive ice create a world at once familiar in its geological logic and alien in its extreme conditions, a vivid testament to the dynamic history of our neighboring planet. Other signs pointing to a wetter past on Mars are etched into its landscape in the form of deltas and alluvial fans, landforms sculpted over eons by flowing water. These structures emerge when rushing currents slow and deposit the sediment they carry, leaving behind intricate fan-shaped patterns that testify to ancient aquatic activity. On Mars, such formations are frequently nestled within craters, hinting that these depressions once cradled lakes, tranquil pockets of water that lingered long enough to shape their surroundings. This narrative of a once watery Mars is reinforced not only by visible landforms, but also by detailed studies of Martian minerals, sedimentary layers, and the contours of its terrain. Further evidence comes from minerals that are incontrovertible markers of water's presence. Hematite and goethite, for instance, have been detected across Mars, and both are known to form primarily in watery environments. In a remarkable discovery in 2004, NASA's Opportunity rover unearthed jarosite, a mineral that forms exclusively in acidic water, delivering conclusive proof that liquid water once flowed across the Martian surface. Just a few years later, in 2007, the Spirit rover revealed large deposits of silica, another mineral that only crystallizes in wet conditions, reinforcing the emerging picture of a planet shaped by water. By December 2011, Opportunity had added gypsum to the list, a mineral that forms in watery environments, further solidifying the evidence of Mars's aquatic past. Scientists even speculate that water exists deep below the surface, locked within the planet's mantle as hydroxyl, a molecule composed of hydrogen and oxygen. Estimates suggest that Mars may harbor as much water internally as Earth does on its surface. If all this hidden water were somehow brought to the surface, it could blanket the entire planet in a layer ranging from 200 to 1,000 meters deep, or roughly 660 to 3,280 feet, a staggering volume by any measure. On March 18, 2013, NASA revealed a groundbreaking discovery from the Curiosity rover. Analysis of Martian rocks uncovered minerals that had once interacted with water, particularly hydrated calcium sulfate. These minerals appeared in rock fragments nicknamed tintina and sutininlia, as well as in tiny veins and rounded formations called nodules in other rocks such as Canner and Vernica. Curiosity's DAN, Dynamic Albedo of Neutrons, instrument detected water hidden beneath the surface, revealing that the soil contained up to 4% water down to a depth of roughly 60 centimeters. This discovery occurred as the rover traveled from its landing site at Bradbury Landing toward Yellowknife Bay in the region known as Glenelg, painting a vivid picture of water's lingering presence in the Martian subsurface. In September 2015, NASA announced evidence of salty liquid water, or brine, flowing seasonally down certain Martian slopes. These dark streaks, known as recurring slope lineae, appear when temperatures rise above -23 degrees Celsius and freeze again when conditions drop. While initially thought to be formed by subsurface liquid water, later research suggested that many of these streaks may instead result from dry, sandy flows with minimal involvement of water. The debate continues, reflecting the complexities of understanding Mars's hydrological history. Another captivating theory suggests that Mars's vast northern plains were once submerged beneath a deep ocean, potentially hundreds of meters in depth. In March 2015, some scientists proposed that this ancient ocean might have been comparable in size to Earth's Arctic Ocean, based on the high levels of deuterium, a heavy form of hydrogen found in the Martian atmosphere. Deuterium on Mars is 5 to 7 times more abundant than on Earth, hinting that the planet once held far more water. Earlier measurements by Curiosity in Gale Crater detected deuterium, but the levels fell short of confirming a full-scale ocean. Additionally, climate models of ancient Mars suggest it may never have been consistently warm enough to sustain vast bodies of liquid water, adding complexity to the debate. Remarkable discoveries extend even to the planet's poles. Near the Martian North Pole lies a massive crater named Korolev, measuring approximately 81 kilometers across and containing about 2,200 cubic kilometers of water ice, a frozen reservoir of staggering proportions. In November 2016, NASA announced the discovery of an immense subterranean ice deposit in Utopia Planitia, containing as much water as Earth's Lake Superior, roughly 12,100 cubic kilometers. Between 2018 and 2021, the European Space Agency's ExoMars Trace Gas Orbiter detected additional signs of subsurface ice within Valles Marineris, one of Mars's largest canyon systems, further revealing a hidden icy landscape beneath the surface. Mars orbits the Sun at an average distance of roughly 230 million kilometers, completing a full orbit, or Martian year, in about 687 Earth days. A single day on Mars, known as a sol, lasts 24 hours, 39 minutes, and 35 seconds, just slightly longer than an Earth day. With an axial tilt of around 25 degrees, similar to Earth, Mars experiences familiar seasonal cycles, but each season stretches nearly twice as long due to the planet's extended year. Presently, Mars's North Pole points toward the bright star Deneb. The planet's orbit is notably elliptical, more so than Earth's, with only Mercury exceeding it in eccentricity. Around 1.35 million years ago, Mars's orbit was far more circular than it is today. These orbital variations occur in cycles lasting approximately 96,000 Earth years. During opposition, when Mars is closest to Earth, this event occurs roughly every 780 days, though the interval can vary between 764 and 812 days. Depending on their respective positions in their orbits, the distance between Mars and Earth can fluctuate from about 54 million kilometers at the closest approach to as much as 401 million kilometers at the farthest. Oppositions coinciding with Mars's perihelion, its closest approach to the Sun, produce perihelic oppositions, moments when the planet appears especially large and luminous in the night sky, as occurred in 2003, 2018, and projected again in 2035. Mars shines with hues of yellow, orange, or deep red, typically slightly dimmer than Jupiter, though it can become the second brightest planet in the night sky at its peak, surpassed only by Venus. When the two planets are closest, Mars appears dramatically larger, yet atmospheric distortion limits ground-based telescopes to resolving surface features around 300 kilometers in width, even under optimal viewing conditions. During periods of retrograde motion, lasting roughly 72 days, Mars seems to trace a backward loop across the sky, an optical illusion resulting from Earth overtaking Mars in its orbit. In the middle of this apparent backward motion, the planet reaches peak brightness, illuminating the night sky with heightened intensity. Mars is orbited by two tiny moons, Phobos and Deimos, both small compared to Earth's moon. Phobos measures about 22 kilometers across, while Deimos spans roughly 12 kilometers, or 7.5 miles. Despite their diminutive size, these moons have long intrigued scientists, with prevailing theories suggesting they were once wandering asteroids captured by Mars's gravity. Both were discovered in 1877 by American astronomer Asaph Hall, who named them after the twin sons of the Greek god of war, Ares, Phobos, the embodiment of panic and fear, and Deimos, the spirit of dread and terror, followers of their father into battle. Later, the Romans adopted the name Mars for their war god, lending the planet its modern title. Even today, in the language of modern Greece, Mars retains the name Eris, echoing centuries of myth and observation. From the crimson plains of the Martian surface, the heavens would appear unlike anything we know from Earth. The two moons of Mars, Phobos and Deimos, perform celestial dances that defy our terrestrial expectations. Phobos, the innermost of the pair, exhibits particularly bizarre behavior. It rises in the west and sets in the east, the reverse of what anyone standing on Earth would anticipate. This tiny moon completes its erratic circuit in just 11 hours, which means a Martian observer could witness it rise and set twice within a single Martian day. Deimos, by contrast, behaves more conventionally, rising in the east like our moon, yet its motion is deceptively slow. Positioned just beyond what astronomers call a synchronous orbit, where a moon would appear to hover steadily in the sky, its languid pace contrasts sharply with Phobos's frantic rush. Phobos itself is gradually being drawn closer to Mars, pulled inexorably by the planet's gravity. Scientists estimate that in around 50 million years, this diminutive satellite may either crash into the Martian surface or shatter under tidal forces, potentially forming a faint ring reminiscent of Saturn's magnificent bands, albeit on a far smaller scale. The origins of Phobos and Deimos have long perplexed astronomers. Their dark, rocky exteriors and the composition of their surfaces bear striking similarities to carbonaceous chondrite asteroids, hinting that they might be captured wanderers from the asteroid belt. Yet this hypothesis is complicated by their near-perfect circular orbits along Mars's equator, an unusual trait for captured celestial bodies whose paths tend to be far more erratic. Another theory suggests that the moons formed through accretion, a process in which dust and rock coalesced early in Mars's history. However, this notion faces its own contradictions, since their chemical makeup aligns more closely with distant asteroids than with the Martian crust. A third, increasingly intriguing possibility proposes that a colossal asteroid once collided with Mars, ejecting fragments of the planet into space. Over time, these fragments could have coalesced, forming Phobos and perhaps even Deimos. Recent studies hint that Phobos is highly porous, with a sponge-like interior containing minerals familiar from Mars itself, lending credence to the idea that it originated from Martian debris. Some scientists even speculate that Mars might once have possessed a larger moon, torn apart by a violent impact, leaving the smaller remnants we now call Phobos and Deimos. It's possible that even smaller, undetected moons, measuring less than 100 meters across, roughly 330 feet, still orbit the planet, alongside a tenuous ring of dust drifting silently between the two moons. Human fascination with Mars stretches back millennia. Every few years, Earth and Mars align in such a way that the red planet draws unusually close to our world, creating prime viewing conditions known as oppositions. Even rarer are perihelic oppositions, like when Mars not only opposes the Sun, but also reaches its closest point to the Sun, making it shine more brilliantly than usual in the night sky. Ancient civilizations noticed this celestial wanderer with awe. The Sumerians named it Nergal, the god of war and disease, whose importance grew over time, eventually becoming the chief deity in the city of Nineveh. Mars was even described in some texts as the star that judged the fate of the dead. Egyptian astronomers, observing centuries later, had already recorded its peculiar retrograde motion by the year 1534, before the Common Era. The Babylonians refined the study of Mars, meticulously tracking its position and predicting its movements. By the era of the Neo-Babylonian Empire, they had identified patterns in its cycles. 37 synodic periods, oppositions occurring over 79 years, equating to 42 loops through the zodiac. Mathematical techniques developed to improve their predictive models demonstrated remarkable sophistication for the time. In ancient Greece, Mars bore names reflecting its fiery persona, from Pyro to Ares, the latter honoring the Greek god of war. The Romans later inherited this association, renaming the planet Mars and connecting it with images of battle, swords, and shields. The great philosopher Aristotle, observing in the 4th century before the Common Era, noticed Mars passing behind the moon, deducing that it lay farther from Earth. In Alexandria, another scholar compiled extensive observations of planetary motions in the Almagest, a text that would dominate European and Middle Eastern astronomy for over 14 centuries. Meanwhile, in China, scholars had long observed Mars, referring to it as the fire star, in accordance with the traditional system of 5 elements called wing. By the 4th century before the Common Era, they were documenting its movements with striking precision. Centuries later, in the 17th century, Tycho Brahe measured the parallax of Mars, how much a planet appears to shift against the background of stars from different points on Earth, laying the groundwork for more accurate distance calculations. Johannes Kepler built upon these measurements, revealing that Mars does not follow a perfect circle around the Sun, but an ellipse, speeding up when nearer to the Sun and slowing when farther away, a motion later explained by fundamental laws of physics. Observers could see Mars even more clearly with telescopes. In 1672, Giovanni Domenico Cassini measured Mars's parallax with unprecedented accuracy, although instruments of the time were still limited. Rare events, such as the occultation of Mars by Venus in 1590, were recorded meticulously, though only once in history. Galileo Galilei in 1610 became the first to glimpse Mars through a telescope, followed by Christian Huygens, who mapped surface features for the first time. By the 19th century, telescopes revealed intricate details of Mars's landscape. During the perihelic opposition of September 5, 1877, Giovanni Schiaparelli created the most detailed map of the planet yet, noting long straight lines called canali, Italian for channels, which, mistranslated as canals, sparked the public imagination about Martian civilizations. Inspired, Percival Lowell constructed massive observatories in the United States using 30 and 45 centimeter telescopes to study Mars intensively, popularizing the idea of advanced life on the red planet. Other astronomers, including Henri-Joseph Perrotin and Louis Thollon in France, contributed to the spectacle, cementing the notion of canals in the public mind. Yet as telescope technology improved, the supposed canals vanished. In 1900, Eugene Antoniadi used an 84 centimeter telescope and observed only irregular patches, dispelling the notion of Martian engineering. The 20th and 21st centuries saw a dramatic transformation in our understanding as robotic spacecraft, rovers, orbiters, and landers traveled to Mars from the United States, the Soviet Union, Europe, India, the United Arab Emirates, and China. These missions mapped the surface, studied the weather, and analyzed geology with unparalleled precision. The first spacecraft to visit Mars, NASA's Mariner 4, launched on November 28, 1964, and flew past the planet on July 15, 1965, capturing the first close-up images of another world. Mariner 4 even detected a weak radiation belt, just 0.1% as strong as Earth's. Subsequent Mariner missions of the 1960s and 1970s shattered earlier assumptions, revealing a barren landscape with no oceans and little hope of life. Later, the Mars Global Surveyor, launched in 1996 and operational until 2006, mapped Mars in unprecedented detail, charting its surface, magnetic fields, and mineral composition, completing a portrait of the red planet that was as detailed as it was transformative. Mars, once a fiery symbol of myth and mystery, had been stripped of its imagined canals and civilizations, yet it emerged richer in reality. Its moons, its orbits, its crimson deserts and dusty plains offering a story of celestial complexity, a narrative written in rock, ice, and orbit, inviting generations of humanity to look upward and wonder anew. And today, anyone with an internet connection can explore the mysterious terrain of Mars without leaving Earth. Interactive maps and tools, some as accessible as Google Mars, allow users to zoom across the red planet's valleys, craters, and dunes. Modern exploration has been driven by a fleet of sophisticated spacecraft like the Mars Reconnaissance Orbiter and the European Space Agency's Mars Express, whose data have transformed our understanding of the planet from blurry sketches to detailed, high-resolution mosaics. NASA has taken this engagement further with platforms like Mars Trek, which offers breathtaking visualizations compiled from 50 years of observations, and Curiosity, a three-dimensional simulator that lets users navigate the Martian surface as if they were riding aboard the Curiosity rover itself. By the year 2023, the red planet was bustling with human-made activity. 10 spacecraft were actively investigating its mysteries, 8 orbiting above and 2 rovers traversing its surface. Orbiters included 2001 Mars Odyssey, Mars Express, Mars Reconnaissance Orbiter, the European-Russian ExoMars Trace Gas Orbiter, the UAE's Hope Orbiter, and China's Tianwen-1. Meanwhile, the rovers Curiosity and Perseverance rolled over Martian plains and cliffs, analyzing rocks, soil, and the subtle hints that Mars might once have supported life. Looking ahead, NASA's ESCAPADE mission is slated for launch in 2025, designed to study the Martian environment in new ways. Europe's Rosalind Franklin rover, intended to hunt for signs of ancient life, has experienced multiple delays, originally set for launch in 2018, but now projected no earlier than 2028. After renewed funding in 2024, the mission has been revived. Beyond these, a joint NASA-European Space Agency effort aims to return Martian samples to Earth, potentially as early as 2026, while China's ambitious Tianwen-3 mission also seeks to return samples in 2030. Mars's surface is now littered with the remnants of past missions. More than 7 tons of debris, including crashed spacecraft and discarded components, scattered across its barren landscape as of February 2024. In April of that year, NASA began exploring commercial partnerships with several companies to support robotic missions, focusing on telecommunications, payload delivery, and high-resolution imaging of the Martian surface. Centuries of speculation about life on Mars paint a fascinating backdrop to modern exploration. In the late 19th century, many scientists imagined Mars as a potentially habitable world, complete with oxygen and flowing water. Yet in 1894, W. Campbell, working at Lick Observatory, concluded that if water vapor or oxygen existed, it was in quantities too minuscule to detect with the instruments of the time. Campbell's findings were met with skepticism, but he and V.M. Slipper repeated the study in 1909 using improved equipment, arriving at the same conclusion. Finally, in 1925, W.S.A. Adams confirmed these results, definitively challenging the idea that Mars resembled Earth. Even so, speculation about Martian life persisted well into the 1960s, fueled by misinterpretations of seasonal changes on the planet's surface. Today, scientists define planetary habitability primarily by the presence of liquid water. For a planet to sustain it, its orbit must fall within the habitable zone around its star, where temperatures allow water to remain liquid. For our Sun, this zone stretches from Earth's orbit to just beyond Mars. During its closest approach to the Sun, known as perihelion, Mars briefly enters this zone, but its thin, low-pressure atmosphere prevents water from remaining liquid over large areas for long periods. Evidence from ancient riverbeds, dried lakes, and mineral deposits suggests that water did once flow on Mars, hinting at a more hospitable past. Yet, recent analyses indicate that this water may have been too salty and acidic to support life as we know it. Mars's environment is harsh and unforgiving. Its surface conducts heat poorly, leaving temperatures fluctuating dramatically. The absence of a protective magnetosphere exposes it to relentless solar wind, while its thin atmosphere ensures that water quickly sublimates into gas. Geologically, the planet is largely dormant, with volcanic activity long ceased, meaning that essential processes that recycle chemicals and minerals between the crust and mantle are no longer active. This makes the search for past or present life a challenge. In the mid-1970s, NASA's Viking missions attempted to answer this question directly, conducting experiments at landing sites to detect microorganisms in the soil. Initial results hinted at life. When soil samples were exposed to water and nutrients, temporary spikes in carbon dioxide were observed. These findings sparked debate that continues today, with some scientists, including Gilbert Levin, maintaining that life may indeed have been detected. Later studies added layers of complexity. In 2014, the Martian meteorite known as 791 was found to contain high concentrations of chlorate, perchlorate, and nitrate ions. These chemicals, potentially widespread on Mars, suggest that any organic molecules would need to be buried deeply beneath the surface to endure the extreme conditions. Orbiters have also detected trace amounts of methane and formaldehyde, molecules that normally break down quickly in the Martian atmosphere, fueling ongoing questions about possible biological activity. Mars remains a planet of intrigue, a world once imagined to be a mirror of Earth, now revealed as a stark, alien landscape. From orbiters capturing its sweeping vistas to rovers probing its soil millimeter by millimeter, humanity continues its quest to uncover the secrets of this enigmatic neighbor. Each mission adds pieces to a puzzle that stretches back billions of years, hinting at a time when water flowed freely, and the planet's potential for life was far greater than it is today. The story of Mars is both a testament to human curiosity and a chronicle of our relentless pursuit to understand the unknown. However, the story of Martian glass is far more intricate than it first appears. While some glass on Mars may have been created by intense meteor impacts, scientists have learned that it can also form through volcanic or other geological processes. When certain types of rock react under extreme heat and pressure, they can melt and rapidly cool into smooth, shiny surfaces. This dual possibility of formation, both violent and gradual, makes Martian glass a fascinating puzzle for planetary scientists. In recent decades, the discovery of impact glass on Mars has captured particular attention. This is a special type of glass created when meteors strike the planet's surface with tremendous force, instantly melting rock into new forms. On Earth, similar impact glass has sometimes preserved microscopic evidence of ancient life, providing a tantalizing clue for those searching for signs of biology beyond our planet. The implication is clear. If life ever existed on Mars, traces of it might survive within these hardened, glassy relics. In June of 2024, a striking example of such a discovery made headlines. A rock, later named the Chayava Falls Rock, was identified by NASA as a potential biosignature. The Perseverance rover, which has been meticulously exploring the Martian surface, carefully collected a sample from this rock. This sample could one day be returned to Earth, where highly sophisticated laboratory instruments could search for microscopic clues that might confirm whether life ever touched this distant world. Yet despite the excitement, scientists remain cautious. The data gathered so far cannot definitively determine if the rock's features are biological in origin or simply a product of natural, non-living processes. The mystery remains open, urging further exploration. Throughout the 20th and 21st centuries, humans have dreamt of walking on Mars. Numerous mission plans have been proposed, debated, and then shelved, largely due to technological and financial constraints. The NASA Authorization Act of 2017 encouraged studies on sending humans to Mars in the early 2030s, but subsequent reports concluded that the goal was still beyond immediate reach. In parallel, China announced in 2021 its intentions to mount a crewed mission to Mars by 2033, though details remain tentative. Private companies have added an unprecedented dimension to this ambition. SpaceX, for example, has outlined a vision for permanent human settlement on Mars, leveraging the massive Starship launch vehicle development as of 2024. Elon Musk, the company's founder, predicts that within the next 2 decades, a human colony on Mars could begin to take shape. The strategy involves mass-producing starships, transporting initial supplies from Earth, and gradually relying on Mars's local resources until the colony becomes self-sustaining. Launch windows, occurring approximately every 26 months, will play a critical role in timing these missions for maximum efficiency. Ambitious proposals, such as building a space elevator on Phobos, the larger of Mars's 2 moons, have even entered the conversation, highlighting the boldness of long-term plans. Beyond governmental and private ventures, nonprofit organizations like the Mars Society and the Planetary Society continue to champion human exploration. These groups keep public attention focused on the dream of a multiplanetary future, emphasizing both the scientific and cultural significance of expanding human presence beyond Earth. While our ambitions reach outward toward Mars, another celestial neighbor has quietly drawn scientific curiosity. Proxima Centauri, the star nearest to our Sun. Located about 4¼ light-years away, it occupies a position in the southern sky within the constellation Centaurus. Discovered in 1915 by astronomer Robert Innes, Proxima Centauri is deceptively small and faint. Its apparent magnitude of 11.13 renders it invisible to the naked eye, requiring a telescope for observation. Its name, derived from Latin, literally means nearest of Centaurus. Proxima is part of a larger stellar system called Alpha Centauri and is specifically known as Alpha Centauri C. It lies roughly 2.18 degrees southwest of the main binary pair Alpha Centauri A and B. At this distance, about 12,950 astronomical units, a full orbit around its companions would take roughly 550,000 Earth years. Classified as a red dwarf, Proxima Centauri possesses only about 1/8 the mass of our Sun, but is far denser, with a density around 33 times greater. Thanks to its proximity, scientists have been able to measure Proxima Centauri's size with remarkable precision. Its diameter is approximately 1/7 that of the Sun, or around 14%. Despite its modest, steady glow, Proxima is also a flare star. Occasionally, it erupts in powerful bursts of magnetic energy, producing brief but intense brightening events that can emit X-rays comparable in intensity to those of our Sun. Inside Proxima, energy is transported from the core to the surface through convection, a continuous circulation of hot plasma rising and cooler material sinking. This process allows the star to efficiently use almost all of its hydrogen fuel. Unlike our Sun, which will exhaust much of its hydrogen before leaving the main sequence, Proxima Centauri is expected to burn steadily for an astonishing 4 trillion years, a cosmic timescale almost beyond comprehension. Planets orbiting Proxima Centauri have also drawn significant attention. The confirmed planet, Proxima Centauri b, orbits a mere 7.5 million kilometers from the star, completing one orbit in just over 11 Earth days. Slightly more massive than Earth, it exists in the so-called habitable zone, where temperatures could theoretically allow liquid water. However, Proxima's frequent flares raise questions about whether life could endure such intense stellar activity. Additional candidates, Proxima Centauri c and d, orbit farther out and closer in, respectively, but their status remains tentative. Proxima Centauri is classified as an M555 star on the Hertzsprung-Russell diagram, a designation indicating a cool, low-mass star with a reddish-yellow hue. Its surface temperature hovers around 3,000 degrees Kelvin. If observed from a distance of 33 light-years, it would appear extremely dim, with an absolute visual magnitude of 15.5. Most of its radiation, over 85%, emerges as infrared light, invisible to human eyes. Measurements using advanced techniques like optical interferometry and microlensing have revealed Proxima's diameter and mass with increasing accuracy. Its density is immense compared to the Sun, and surface gravity is extraordinarily strong, about 162 times what we experience on Earth. Rotation periods have been refined over time, settling around 90 Earth days. The star's interior, entirely stirred by convection, distributes helium from fusion evenly, stabilizing the star over its extraordinarily long lifespan. Magnetic activity inside Proxima generates flares lasting from seconds to minutes, briefly illuminating the star in sudden bursts of energy. This delicate dance of energy, gravity, and magnetism, combined with its neighboring planets and remarkable longevity, makes Proxima Centauri a subject of intense scientific study. From the glassy relics of Mars to the faint, flaring light of our closest stellar neighbor, humanity's gaze continues to stretch outward, chasing knowledge across the cosmic ocean. On the 6th of May, 2019, a remarkable event unfolded in the depths of our cosmic neighborhood. One of the most intense flares ever recorded from Proxima Centauri erupted, illuminating space with a sudden surge of energy. This eruption unleashed an extraordinary torrent of ultraviolet light, estimated at around 2 followed by 30 zeros in units of energy known as ergs. To put that into perspective, the energy released was sufficient to heat the surrounding plasma to an unimaginable 27 million degrees Kelvin, a temperature so extreme that it naturally generated powerful X-rays. Under typical conditions, when Proxima Centauri appears calm, its X-ray output hovers between 4 and 16, followed by 26 ergs per second, a range that is surprisingly comparable to the energy output of our own Sun. Yet during moments of intense flaring, the star's X-ray brightness can skyrocket to 10, followed by 28 ergs per second, a staggering leap that underscores the star's incredible dynamism. The key to this activity lies in Proxima's outer layer, the chromosphere, a realm of plasma roiling with magnetic energy. Astronomers can observe this restlessness directly in the star's light spectrum, most notably through a striking bright line produced by magnesium atoms that have lost a single electron. This luminous signature shines at a wavelength of 280 nanometers, far beyond the reach of human vision, offering scientists a window into the star's ceaseless energy. Researchers estimate that as much as 88% of Proxima Centauri's surface may be actively flaring or glowing at any given moment, a figure that dwarfs the activity observed on the Sun. Even when the star seems relatively tranquil, The constant magnetic turbulence maintains its corona, the outermost layer, at a scorching 3 to 12 million degrees Kelvin. By comparison, the Sun's corona typically hovers around a more modest 2 million degrees. Despite its smaller size, Proxima emits nearly as much X-ray energy as the Sun, a testament to the immense energy packed into this compact red dwarf star. Among its stellar peers, however, this level of activity is actually considered moderate. This aligns with estimates of Proxima's age, roughly 4,850,000,000 years, a period during which red dwarfs gradually slow their rotation and temper their flaring over billions of years. Intriguingly, Proxima's activity is not constant, but appears to follow a repeating cycle, lasting approximately 442 days, far shorter than the Sun's 11-year solar cycle. Beyond flares and radiation, the star emits a stellar wind, a flow of charged particles that, while modest compared to the Sun, still results in a surprisingly high rate of material loss from each square meter of its surface, up to 8 times greater than the Sun. Despite these energetic outbursts, Proxima Centauri's long-term prospects are extraordinary. Burning its nuclear fuel at a slow pace, it is expected to remain on the main sequence, its current phase of stable hydrogen fusion, for an astonishing 4 trillion years. Over time, it will gradually convert hydrogen into helium, causing its core to contract slightly and its surface temperature to rise. In the distant future, Proxima will transform into a blue dwarf, shining more intensely, up to 2.5% as bright as the Sun, and potentially warming nearby planets for billions of years. Unlike the Sun, Proxima will not swell into a red giant. Instead, it will quietly fade into a helium white dwarf, gradually cooling over eons. The star's connection to the Alpha Centauri system remains a subject of scientific investigation. One hypothesis suggests that during the early formation of this stellar neighborhood, Proxima, a low-mass star, was gravitationally captured by the stronger pull of Alpha Centauri A and B. If this were true, Proxima would likely share similar chemical composition with its larger companions, and its gravity could have influenced the distribution of material in the disks around A and B, potentially aiding in the formation of planets. An alternative scenario proposes that Proxima was captured later during a close encounter with the system, initially orbiting chaotically before the gravitational influences of the Milky Way and nearby stars stabilized its path. Depending on which scenario is accurate, Proxima's planets may have experienced more or less gravitational disturbance over time. Today, Proxima Centauri is about 4.24 light-years from the Sun, approximately 268,500 times the distance between Earth and the Sun. Observed from Earth, it sits just over 2 degrees from Alpha Centauri in the sky, roughly 4 times the apparent diameter of the full moon. Its motion is noticeable, shifting across the celestial sphere by roughly 3.85 arcseconds each year, and it is approaching our solar system at a speed of 22.2 kilometers per second. From a planet orbiting Proxima, our Sun would appear as a bright star in the constellation Cassiopeia, comparable in brilliance to stars like Achernar or Procyon as seen from Earth. For the past 32,000 years, Proxima has held the title of the closest star to the Sun, a distinction it will retain for about 25,000 more. In the distant future, Alpha Centauri A and B will alternate as the nearest stars, swapping positions roughly every 79.91 years. Predictions indicate that Proxima will reach its absolute minimum distance from the Sun in about 26,700 years, coming just over 3 light-years away. Proxima Centauri orbits the Milky Way at a distance that varies between 27,000 and 31,000 light-years, tracing a slightly elongated, gently wobbling path around the galactic center. The star was first linked to Alpha Centauri A and B in 1915, earning the designation Alpha Centauri C, with subsequent observations confirming that all 3 stars are gravitationally bound. Proxima's orbit around the binary pair is vast and stretched out, taking roughly 547,000 years to complete a full cycle. During this journey, it swings as close as 4,300 astronomical units and as far as 13,000 astronomical units. Currently, it is near its farthest point, approximately 12,947 astronomical units away, equivalent to nearly 1.94 trillion kilometers. Proxima is not traveling alone. It shares its general motion through space with 6 other stars, 2 binary systems, and a triple star system, suggesting that they may all have originated from the same stellar cluster. As of 2022, astronomers have confirmed 3 planets orbiting Proxima Centauri, offering tantalizing possibilities for the study of planetary systems around red dwarf stars. Its story continues to unfold, a compelling saga of energy, motion, and celestial endurance in the quiet yet dynamic reaches of our galactic neighborhood. And so begins the long, twisting story of humanity's fascination with Proxima Centauri, the nearest known star to our sun, a small and unassuming red dwarf whose unremarkable appearance masks an extraordinary cosmic drama. Over the past century, astronomers have peeled back layer after layer of mystery surrounding this star, and the tale of its planets, real, potential, and disputed, reads like an interstellar detective story. One planet is confirmed, while 2 others linger in uncertainty, their existence hinted at but still under scrutiny. Among the possible worlds circling this tiny star, one may be among the smallest ever detected, using the subtle wobble of a star as a clue. Another, known as Proxima b, has captured imaginations worldwide, a planet remarkably close in size to Earth, orbiting snugly within the star's habitable zone, a region where temperatures could allow for liquid water. The third candidate, Proxima c, lies farther out, possibly a gas dwarf, a frigid world whose reality is still debated among astronomers. The search for planets around Proxima Centauri is not new. It began in the late 1970s, sparked by curiosity over whether this nearby red dwarf might conceal hidden worlds. In the 1990s, scientists employed the radial velocity technique, observing minute wobbles in the star's motion caused by orbiting planets. These early studies began to set constraints on the size of any planets that could exist there, but challenges soon emerged. Proxima Centauri is notoriously active, erupting with stellar flares that complicate the data, making it difficult to distinguish a planetary pull from the star's own erratic behavior. In 1998, the Hubble Space Telescope turned its gaze toward Proxima, employing the Faint Object Spectrograph to probe for planets orbiting roughly half an astronomical unit from the star, the average distance between Earth and the Sun. Initial observations hinted at a possible planet, but subsequent checks using Hubble's Wide Field and Planetary Camera 2 revealed nothing conclusive. Parallel studies using astrometry at the Cerro Tololo Inter-American Observatory, which tracks a star's precise position over time, ruled out the presence of a Jupiter-sized planet orbiting between 2 and 12 Earth years. It was not until 2017 that another breakthrough occurred. Astronomers using the Atacama Large Millimeter/Submillimeter Array, or ALMA, detected a cold dust belt encircling Proxima Centauri, spanning 1 to 4 astronomical units. This dust, chillingly cold at around 40 Kelvin, far colder than anything found on Earth, held a mass roughly 1% that of our planet. 2 more intriguing features emerged: a second, even colder dust belt around 30 astronomical units, and a mysterious object emitting light at a slight distance from the star. Early excitement suggested these might point to hidden planets, but closer analysis revealed that a massive flare in March 2017 likely accounted for most of the signals. The discovery that truly captured global attention was Proxima Centauri b. Also called Alpha Centauri CB, this planet orbits astonishingly close to its star, a mere 0.05 astronomical units, or roughly 7.5 million kilometers, much closer than Mercury is to the Sun. Completing one orbit in just over 11 Earth days, its mass is estimated at a minimum of 1.07 times that of Earth. Temperatures could be conducive to liquid water, positioning it squarely within the star's habitable zone. The initial hints of Proxima b emerged in 2013 when astronomer Mikko Tuomi reanalyzed archival data. Confirmation arrived in 2016 through the Pale Red Dot Project, led by a team of 31 scientists under Guillaume Anglada Escudé at Queen Mary University of London. Their findings, published in Nature, relied on precise measurements from HARPS on the European Southern Observatory's 3.6-meter telescope at La Silla Observatory and UVS on the 8-meter Very Large Telescope Paranal Observatory. Attempts to observe Proxima b transiting its star, a phenomenon where a planet passes in front of the star, causing a temporary dimming, have largely been inconclusive. One potential transit signal was detected on September 8, 2016, by a telescope in Antarctica, but the evidence fell short of certainty. In the same study that confirmed Proxima b, scientists noticed another mysterious signal, with periods ranging from 60 to 500 days, though it remained unclear whether it indicated a second planet or simply the star's erratic behavior. This uncertainty gave rise to Proxima Centauri c, orbiting much farther out, around 5 astronomical units, or 220 million kilometers from the star, completing a full orbit in approximately 1,900 days, or just over 5 Earth years. Estimated to be a super-Earth or small gas giant, its mass could be about 7 times that of Earth. Compared to Proxima b, this distant world is far colder, around 39 Kelvin, making it an inhospitable place unlikely to support life as we know it. Initial signals pointing to Proxima c appeared in April 2019, detected by Mario Damaso and his team through subtle stellar motions captured by HARPS. Follow-up observations, including infrared imagery from Hubble's Sphere Telescope, suggested that the planet might even have a Saturn-like ring system, but the evidence was blurred and contested, with skepticism resurfacing in 2022. Meanwhile, an even smaller candidate planet emerged in 2019 with a rapid orbit of 5.15 days and a mass about 0.29 times that of Earth. By February 2022, this signal was confirmed as a potential planet, adding another layer of intrigue to Proxima Centauri's planetary system. Before any of these discoveries, the idea of habitable worlds around Proxima Centauri had already captured the imagination of science communicators and the public. Documentaries such as Alien World speculated about planets in the star's habitable zone, which spans from 0.023 to 0.054 astronomical units. Such planets would orbit extremely quickly, completing a year in just 3.5 to 14 Earth days. Tidal locking, a phenomenon where one side always faces the star, would create stark contrasts between eternal day and night. Yet a thick atmosphere could redistribute heat and moderate the extremes. Stellar flares pose another challenge, potentially stripping atmospheres, but scientists like Georg Zabriskie of the University of California, Berkeley suggest that a strong magnetic field could shield life from the star's harmful radiation. The history of Proxima Centauri itself stretches back over a century. In 1915, Scottish astronomer Robert Innes, working at the Union Observatory in Johannesburg, identified a faint star moving through space in tandem with Alpha Centauri, suggesting it be named Proxima Centauri, the nearest of Centaurus. In 1917, Dutch astronomer Joan Voet confirmed its proximity using trigonometric parallax. Subsequent measurements in 1928 by Harold Alden cemented Proxima Centauri as the closest star to our solar system, a faint neighbor that nonetheless loomed large in scientific studies. By the mid-20th century, astronomers had also characterized Proxima Centauri as a flare star. Harlow Shapley's observations in 1951 revealed sudden bursts of brightness, and later space-based telescopes, including Einstein Observatory, Exosat, Rosat, and ASCA, documented X-ray flares with increasing precision. Even in recent years, XMM Newton and Chandra have maintained a watchful eye on the star, capturing its energetic eruptions in remarkable detail. Proxima Centauri's location deep in the southern sky restricts visibility to latitudes south of 27 degrees north. Its faint red glow, magnitude 11, renders it invisible to the naked eye, requiring a telescope with a lens at least 3 inches wide for casual viewing. In 2016, the International Astronomical Union formally recognized its name, and later that year, astronomers observed a superflare that increased the star's brightness 68 times over its usual luminosity. Even spacecraft like New Horizons have glimpsed Proxima Centauri from afar, capturing parallax shifts that underscore both our technological reach and the vast distances of interstellar space. Its proximity has fueled speculation about future interstellar missions, with this unassuming red dwarf offering a tantalizing destination for humanity's first ventures beyond the solar system. In the end, Proxima Centauri is far more than a faint point of light. It is a cosmic puzzle, a laboratory for planetary discovery, and a symbol of human curiosity. From the earliest telescopic measurements to the cutting-edge discoveries of its planets, the story of Proxima Centauri continues to unfold, each observation bringing us a little closer to understanding the worlds that might orbit our nearest stellar neighbor. However, if we depend solely on the propulsion technologies currently available, excluding anything nuclear, the prospect of reaching even the nearest star becomes almost unfathomably slow. Traveling to Proxima Centauri, for instance, would take a span of time so vast it stretches the imagination, thousands of years. To put this in perspective, consider the Voyager 1 spacecraft, launched decades ago and now hurtling through the cosmos at a speed of roughly 17 kilometers per second, which translates to about 38,000 miles per hour. Even at this remarkable velocity, if Voyager 1 were aimed perfectly at Proxima Centauri, and if the star itself remained completely stationary, a highly unlikely scenario, it would still require nearly 74,000 years to complete the journey. This reality underscores the staggering scale of interstellar distances and the limitations of conventional propulsion. Yet the human mind has never been content to simply accept such constraints. Visionaries and scientists have long dreamed of faster means of traversing the void between stars. One of the most intriguing concepts is nuclear pulse propulsion. This approach envisions propelling a spacecraft by detonating a series of small nuclear explosives behind it, effectively using controlled blasts as a propulsion method. With such a system, reaching Proxima Centauri might shrink from tens of millennia to roughly a century, a timescale far more manageable in human terms. Ambitious projects inspired by this idea, including Project Orion, Project Daedalus, and Project Longshot, have explored its potential, each presenting its own unique approach to harnessing nuclear energy for interstellar travel. In the modern era, one of the most audacious proposals is Breakthrough Starshot. Launched in the 21st century, this project aims to send minuscule probes to the Alpha Centauri system. These probes would be accelerated to 20% the speed of light, pushed by a colossal array of Earth-based lasers with a combined output of 100 gigawatts. If all goes according to plan, these tiny explorers could pass Proxima Centauri within 2 decades of departure and potentially enter orbit around the star system after roughly 140 years, depending on their navigational precision. Once in the system, they would gather unprecedented data, photographing planets, analyzing atmospheres, and studying the stars themselves. The information collected would then embark on its long return journey to Earth, taking slightly over 4 years to traverse the vast interstellar distance. Back closer to home, the International Space Station, or ISS, stands as humanity's crowning achievement in sustained space habitation. Orbiting in low Earth orbit, the ISS is the largest structure ever constructed in space and is the product of an extraordinary international collaboration. NASA from the United States, Roscosmos from Russia, the European Space Agency, Japan's JAXA, and Canada's CSA pooled their expertise, resources, and ambitions to build, maintain, and operate this orbiting laboratory. Countless partners and contractors across the globe contributed to its assembly, ensuring that the ISS could serve as both a scientific outpost and a symbol of international unity. The primary purpose of the ISS is to provide a unique environment for scientific inquiry in microgravity, the incredibly weak gravitational field found in orbit. Experiments conducted here reveal how physical phenomena and biological systems behave when the familiar pull of Earth is removed, offering insights impossible to gain on the planet's surface. It also allows researchers to understand the effects of long-term space habitation on humans and other life forms. Structurally, the station is divided into 2 main segments: the Russian orbital segment, developed by Roscosmos, and the United States orbital segment, which is the collaborative effort of the US, Europe, Japan, and Canada. A striking feature of the ISS is its massive integrated truss, a framework that supports the station's enormous solar panels and radiators while connecting them to the core modules. These modules serve a variety of purposes: scientific laboratories, living quarters, storage, control centers, and airlocks for spacewalks. The station is equipped with 8 docking ports for visiting spacecraft and orbits approximately 400 kilometers, or 250 miles above Earth. Completing a full orbit in just 93 minutes, it circles the planet more than 15 times each day. The ISS owes its existence to the merging of two earlier space station concepts, the United States Space Station Freedom and Russia's Mir 2. Following years of planning, the first module of the ISS was launched in 1998 using both Russian Proton and Soyuz rockets and NASA's Space Shuttle. On November 2, 2000, Expedition 1 arrived, marking the start of continuous human presence in space, a record that, by March 2024, had lasted over 24 years and involved 279 astronauts from 22 countries. The station is projected to operate until at least 2030, with new modules like the Payload Power Thermal Module from Axiom Space planned to join the orbiting complex. After 2030, a carefully orchestrated deorbiting plan will safely guide the ISS back into Earth's atmosphere with assistance from NASA spacecraft. The vision for international collaboration in space emerged in the early 1970s as the heated competition of the space race between the United States and the Soviet Union began to subside. The 1975 Apollo-Soyuz test project, which brought together astronauts and cosmonauts from these rival nations for a historic docking in orbit, demonstrated the possibilities of cooperation. Inspired by this success, plans like International Skylab and the Skylab Salyut Space Laboratory were proposed, though most were abandoned in the late 1970s due to budget constraints and renewed geopolitical tensions. In the 1980s, the United States embarked on the Freedom Project, a modular space station intended to rival Soviet achievements. By the mid-1980s, both Europe and Japan had joined the effort, proposing the Columbus Laboratory and the Japanese Experiment Module, respectively. However, rising costs in the early 1990s forced Congress to push NASA toward greater international collaboration, while the collapse of the Soviet Union left Russia unable to complete its Mir 2 project independently. In a landmark decision, the United States and Russia joined forces in 1993, announcing a unified plan to build a single joint space station, laying the foundation for what would become the ISS. Prior to its launch, the shuttle program conducted collaborative missions with the Mir station, honing the operational expertise needed for a multinational endeavor in orbit. When originally conceived, the ISS was envisioned not merely as a laboratory, but as a multi-purpose outpost, an observatory, a manufacturing hub, and a waypoint for future lunar, Martian, and asteroid missions. While some of these ambitions remain aspirational, additional roles have been integrated over time. By 2010, U.S. policy explicitly highlighted the ISS as a platform to foster commercial space initiatives, strengthen international relations, and provide educational opportunities. The station's advantages are clear: continuous electricity, reliable data transmission, temperature regulation, and life support allow experiments to be conducted with a precision unattainable on Earth. Unlike unmanned spacecraft, the ISS enables scientists to monitor experiments over extended periods, make adjustments, and incorporate new equipment sent up on supply missions. On board, astronauts pursue research across a wide spectrum of fields, from astrobiology and astronomy to physics, materials science, space weather, meteorology, and human physiology. Their work expands our understanding of both space and life. Earth-based researchers receive data in near real time, facilitating iterative experimentation and immediate refinement. Each new crew rotates every few months, with teams of 6 contributing approximately 160 hours of labor per week, ensuring the station remains a hub of continuous discovery and innovation. This living laboratory, orbiting silently above our world, is not merely a testament to human ingenuity, but a beacon of what can be achieved when nations collaborate beyond borders, united by the shared pursuit of knowledge and the boundless curiosity that drives us to explore the universe itself. However, much of the day-to-day existence aboard the International Space Station is not about groundbreaking discoveries or spectacular spacewalks. It revolves around the meticulous and sometimes monotonous task of keeping the orbiting laboratory operational. Astronauts dedicate hours to maintenance, troubleshooting equipment, cleaning, monitoring systems, and performing routine repairs, ensuring that every component, from life support to communication arrays, functions flawlessly. Yet, Within this continuous cycle of upkeep lies an environment where some of the most extraordinary science of our era is unfolding, a stage where humanity pushes the boundaries of knowledge while circling the Earth at nearly 5 miles per second. One of the most fascinating experiments aboard the ISS is the Alpha Magnetic Spectrometer, commonly known as the AMS. This extraordinary instrument is a particle physics detector, a sentinel in space designed to probe the universe's deepest mysteries. Launched into orbit to hunt for elusive cosmic phenomena, the AMS seeks evidence of dark matter, the invisible substance thought to comprise a large portion of the cosmos, yet never directly observed. Dark matter is one of the great enigmas of modern astrophysics. It shapes galaxies, influences the motion of stars, and remains undetectable by conventional means. NASA has hailed the AMS as a scientific tool as consequential as the Hubble Space Telescope, with capabilities that demand the unique conditions offered only by the ISS. Unlike satellites, which can operate independently, the AMS requires substantial power and a steady stream of data transmission that only the station can provide. On the 3rd of April, 2013, the scientific community was electrified by the announcement of a potential breakthrough. Data from the AMS suggested an unexpected surplus of high-energy particles known as positrons within cosmic rays heading toward Earth. While far from conclusive, these anomalies hinted at the tantalizing possibility that dark matter might be interacting with the visible universe, a discovery that, if confirmed, could rewrite our understanding of matter itself. Life in space, however, is not merely an abstract concept of particles and cosmic rays. It is an extreme and unforgiving environment. Space lacks air, exposes its inhabitants to intense radiation from both the sun and deep space, and oscillates between blistering heat and freezing cold. Gravity is so weak that humans feel as though they are perpetually floating. Remarkably, some life forms have adapted to survive in this harshness. Extremophiles, hardy microorganisms, and tardigrades, microscopic creatures sometimes called water bears, can endure the vacuum of space, surviving complete dehydration, a state known as desiccation. These tiny pioneers provide critical insight into the resilience of life beyond our planet. The ISS also serves as an unparalleled laboratory for understanding how the human body copes with long-term spaceflight. Prolonged exposure to microgravity triggers profound physiological changes. Muscles weaken, bones lose density, and bodily fluids shift toward the head, affecting vision and circulation. Such changes could pose serious risks for astronauts attempting to land on other planets. Research conducted as early as 2006 indicated that a 6-month mission in space could leave astronauts vulnerable to bone fractures and mobility issues upon arriving on a planet like Mars. To mitigate these risks, medical experiments aboard the station, performed under the guidance of the National Space Biomedical Research Institute, focus on innovative diagnostic techniques. One notable study, the Advanced Diagnostic Ultrasound in Microgravity experiment, empowers astronauts to perform complex ultrasound scans while communicating with physicians on Earth. This remote diagnostic method ensures that even in the absence of a doctor on the station, potential health issues can be identified and addressed. The implications extend far beyond space. Such techniques could revolutionize medical care in isolated or underserved regions on Earth, bringing advanced diagnostic capabilities to remote villages, disaster zones, or military outposts. In August of 2020, scientists uncovered a remarkable survival story. A strain of resilient bacteria, Deinococcus radiodurans, had survived 3 years in the vacuum of outer space. Known for its extraordinary resistance to radiation and extreme conditions, this discovery lent credence to the theory of panspermia, the notion that life could travel between planets aboard meteoroids, dust, or spacecraft. These findings suggest that life might not be confined to a single world, but could traverse the cosmos under the right circumstances. During the 2010s, research aboard the ISS expanded exponentially, particularly after the completion of the U.S. segment of the station in 2011. Over more than 2 decades, the station has become a hub for Earth and space science, studying atmospheric components such as aerosols, ozone levels, lightning, and various chemical compounds. Simultaneously, the ISS has served as an observatory for cosmic phenomena, Solar activity, cosmic rays, space dust, antimatter, and dark matter have all been subjects of meticulous study. Specialized instruments such as the Orbiting Carbon Observatory 3, ISS RapidScat, EcoStress, the Global Ecosystem Dynamics Investigation, and the Cloud Aerosol Transport System have provided invaluable data, while devices like the Solar Telescope, Neutron Star Interior Composition Explorer, Calorimetric Electron Telescope, Monitor of All-Sky X-ray Image, MAXI, and the Alpha Magnetic Spectrometer have illuminated the unseen corners of the universe. While gravity on the station is roughly 90% that of Earth's surface, objects inside appear weightless. This sensation of perpetual floating arises because the ISS is in constant free fall around the planet, producing what scientists call microgravity. Yet, this weightlessness is subtly perturbed by air drag, vibrations from equipment, movement of crew members, gyroscopes controlling orientation, thruster firings, and minute variations in gravitational pull across the station, known as tidal effects. Researchers study how these conditions influence the growth of plants, development of animals, formation of protein crystals, and even the engineering of three-dimensional human tissues, discoveries that hold immense promise for medicine and biotechnology. Microgravity also transforms the behavior of liquids, which mix and interact in unexpected ways, offering insights into fluid dynamics that cannot be replicated on Earth. Chemical reactions often proceed more slowly in space, especially under low-temperature conditions, providing unique opportunities to study superconductivity and other phenomena where materials conduct electricity without resistance. Materials science aboard the ISS investigates how to produce stronger, lighter, or more adaptable substances, with potential applications ranging from industrial design to next-generation technology. Even the study of fire has a place in orbit. By observing combustion in microgravity, scientists hope to improve fuel efficiency, reduce pollution, and optimize energy use on Earth. Beyond the laboratory, the ISS functions as a training ground for future missions to the Moon, Mars, and beyond. Astronauts gain hands-on experience in operating, repairing, and maintaining spacecraft under conditions far removed from Earth. This practical expertise reduces risks for long-duration expeditions and accelerates the development of technologies essential for interplanetary exploration. Equally important is the human factor. Life in a confined environment with a small crew for months or years tests mental resilience and social dynamics. The European Space Agency has simulated such conditions on Earth through programs like Mars 500, keeping crews in isolated capsules for extended periods to study psychological effects. Insights from these experiments complement the ISS's research, which focuses on physiological and environmental challenges, offering a holistic picture of long-term space habitation. International cooperation has been central to the station's success. In 2009, space expert Sergei Krasnov emphasized the unparalleled benefits of multinational collaboration. Pooling expertise, resources, and technologies allows humanity to achieve goals far beyond what any single nation could accomplish alone. The ISS exemplifies this principle, advancing scientific understanding, preparing for lunar and Martian missions, and fostering global teamwork. Plans for future interplanetary ventures envision even broader collaboration, potentially including nations such as China, India, and South Korea. While political and legal frameworks like U.S. laws requiring congressional and federal approval for cooperation with China pose challenges, the vision remains clear. Humanity's journey into space is most effective as a shared endeavor. In this extraordinary environment of constant maintenance, high-stakes experimentation, and international collaboration, the International Space Station remains a beacon of human ingenuity. Every orbit, every measurement, every experiment aboard its steel and aluminum corridors contributes to a growing understanding of life, the universe, and our place within it. It is a laboratory, a home, a platform for discovery, and above all, a testament to the remarkable achievements possible when curiosity meets courage, persistence, and cooperation in the vast expanse of space. And so, life aboard the International Space Station stretches far beyond the confines of pure scientific research. Astronauts floating in microgravity serve not only as explorers of space, but as living bridges to the curious minds of students scattered across Earth. They bring science down to a human scale, running experiments designed by young learners, performing captivating science demonstrations, and even engaging in real-time conversations with classrooms through radio signals and email messages. These connections allow students to witness firsthand how research unfolds in an environment vastly different from their own. In many classrooms, teachers encourage students to replicate these experiments, creating a miniature laboratory that mirrors the incredible conditions aboard the ISS. Across Europe, the European Space Agency has opened a treasure trove of free educational resources for teachers. Among these is an immersive lesson where students navigate a three-dimensional digital model of the space station, exploring every corridor, module, and observation window. Beyond exploration, they face surprise challenges designed to mimic the decision-making and problem-solving tasks astronauts confront daily, giving students a taste of life in orbit. Similarly, Japan's space agency, JAXA, invests heavily in programs aimed at sparking a passion for science and space among young learners. Their initiatives focus not only on scientific knowledge, but on fostering a sense of responsibility and pride in work, emphasizing how human actions, both on Earth and in space, carry weight and significance. One standout example of JAXA's educational ingenuity is the Seeds in Space experiment, where sunflower seeds spend roughly 9 months aboard the ISS before being returned to Earth to grow. Students and scientists alike study these seeds to understand how the unique environment of space, its microgravity, radiation, and isolation, affects living organisms. Between 2008 and mid-2010, researchers from more than a dozen Japanese universities conducted a wide variety of experiments aboard the station, from biology to material science, all contributing to a deeper understanding of life beyond Earth. The ISS also serves as a stage for cultural expression and creativity. Tetsuo Tanaka, a director at JAXA, once reflected that space has a power to move people emotionally, reaching those with no prior interest in science. Programs like ARIS, amateur radio on the International Space Station, extend this reach, allowing students worldwide to speak directly with astronauts via amateur radio. In regions where radio contact isn't feasible, calls are routed through ground stations connected to speakerphones, ensuring accessibility. The experience often ignites interest in science, technology, engineering, and mathematics, nurturing the next generation of innovators. ARIS teams include participants from 9 countries, spanning Europe, Japan, Russia, Canada, and the United States, highlighting the global nature of space education. Storytelling and media projects have also brought the wonders of the ISS to the public. In 2011, the documentary First Orbit retraced Yuri Gagarin's historic first journey around Earth using the ISS to replicate his orbital path. ESA astronaut Paolo Nespoli filmed the breathtaking footage, complemented by authentic audio from Gagarin's original flight sourced from the Russian State Archive. That same year, the film was made freely available on YouTube, allowing audiences worldwide to experience the view of Earth as a pioneering cosmonaut once did. In a different blending of art and science, astronaut Chris Hadfield produced a music video aboard the ISS in May of 2013, marking the first music video ever filmed in space. Later, in 2021, the virtual reality exhibit The Infinite invited viewers to immerse themselves in the daily life of astronauts, exploring the station in unprecedented detail from the comfort of Earth. The construction of the ISS itself stands as a monument to international collaboration. Modules were crafted in multiple countries. Russia contributed Zarya and Zvezda, with Zvezda originally built in 1985 for a station that never launched. The United States developed Destiny, Unity, the massive truss structures, and solar arrays, all assembled and readied at NASA facilities in Alabama, Louisiana, and Florida. Europe provided the Columbus Laboratory, Japan contributed the Kibo module, and Canada partnered with the US to create robotic systems such as Canadarm2 and Dextra. Together, these components converged in space to form a singular station, with assembly officially commencing in November of 1998. The station's early construction involved Russian modules launching and docking autonomously, while subsequent modules were transported by the Space Shuttle, connected either through robotic arms or spacewalks, known as extravehicular activities. By June 5, 2011, astronauts had conducted over 159 spacewalks, spending more than 1,000 hours outside the protective confines of the station. The first module, Zarya, launched on November 20th, 1998, providing essential systems like power, steering, and communication. 2 weeks later, Unity linked to Zarya, marking the beginning of the Russian-American partnership in orbit. However, these initial modules lacked life support systems, meaning the station could not yet host a permanent crew. That milestone came with the launch of Zvezda in July 2000, enabling a continuous human presence aboard the ISS. Expedition 1, the first crew, arrived in November via the Soyuz TM-31 spacecraft, setting the stage for an enduring human outpost in low Earth orbit. Over the following years, the ISS expanded steadily. Shuttle missions STS-92 and STS-97 added the integrated truss structure, enhancing communication, stability, and solar power generation. New modules and robotic systems arrived through a combination of Russian Soyuz rockets and space shuttle missions. Yet construction faced setbacks, notably the tragic loss of Columbia in 2003, which temporarily paused shuttle flights. Building resumed in 2006 with STS-115 and continued through subsequent missions, each contributing vital components like additional solar panels, science laboratories, airlocks, and observation modules. By February 2011, with the installation of the Leonardo module, the station's American segment reached near completion. Later Russian additions, such as the NA and Pchal modules in 2021, coupled with the European robotic arm, further augmented the station's capabilities. As of February 2025, the ISS boasts 43 distinct modules and elements, each a testament to human ingenuity, resilience, and cooperation. It is a living laboratory, a classroom, a cultural stage, and a beacon of what nations can achieve when they unite under a shared vision. From inspiring young minds with hands-on science to hosting astronauts who live and work in one of humanity's most extraordinary achievements, the ISS remains a symbol of curiosity, creativity, and the limitless potential of exploration. One of the most remarkable aspects of the space station is its modular design, a feature that transforms it into a living, evolving laboratory orbiting Earth. This means that the station can grow and adapt. New modules can be added, old ones removed or repurposed, all to accommodate fresh scientific goals and experiments. At the heart of this flexibility lies its very first piece, Zarya, a name that resonates with the promise of dawn, for in Russian it means sunrise. Launched in the year 1998, Zarya was constructed in Russia, yet the funding came from the United States, symbolizing the international cooperation that would come to define the station. Initially, Zarya bore the crucial responsibilities of power distribution, storage, propulsion, and navigation. As the station expanded over the years, its role shifted. Today, it functions primarily as a storage hub, both internally and in its external fuel tanks, a quiet but vital backbone of the orbital complex. Zarya's design draws its heritage from the Soviet TKS spacecraft, which had been employed during the Salyut space program, linking the station's cutting-edge technology with the legacy of earlier space endeavors. Following Zarya, the American contribution took shape in the form of Unity, also known as Node 1. Unity stands as a symbolic and physical bridge connecting the Russian and American halves of the station. Constructed from steel by Boeing, this round module spans approximately 15 feet in width and stretches nearly 18 feet in length. Its creation took place at NASA's Marshall Space Flight Center in Huntsville, Alabama. Unity was not merely a standalone module, it was the first in a trio of connecting nodes, later joined by Harmony and Tranquility, which together form the core of the United States segment of the station. The Russian section's heartbeat is Zvezda, meaning star in Russian. Launched in July of 2000, Zvezda was the first module to provide full-time habitation capabilities, outfitted with systems for life support and emergency operations. Crafted by RKK Energia and lifted into orbit by a Proton rocket, Zvezda continues to serve as the central command hub for the Russian modules, as well as the designated gathering point for crews during emergencies. Its enduring presence underscores the robustness of early Russian engineering in space. On the American side, Destiny Lab forms the epicenter of scientific research. Launched in February 2001 aboard the Space Shuttle Atlantis during mission STS-98, Destiny connected to Unity over a painstaking 5-day process. This module marked NASA's first permanent laboratory in space since Skylab, enabling astronauts to conduct experiments across a vast range of disciplines, from medicine and physics to engineering and earth sciences. Destiny also houses essential life support systems, including the oxygen-generating apparatus, ensuring that science thrives alongside human survival. Spacewalks, or extravehicular activities, were once complicated operations because American and Russian spacesuits required different support systems. The Quest airlock, launched in July 2001 aboard Atlantis on STS-104, solved this problem. This 20-foot-long module, attached to Unity, includes two distinct areas, one for storing suits and equipment, and another for astronauts to don their gear and exit the station safely. Its installation enabled seamless excursions into the void of space, regardless of the suit nationality. Meanwhile, the Russian segment gained a complementary facility in POS, or Mini Research Module 2, launched on the 10th of November 2009. Acting as an additional airlock, POS allows spacecraft such as Soyuz and Progress vehicles to dock with the station. It also facilitates fuel transfers and provides storage for Russian Orlan spacesuits. Safety was a paramount concern in its design, with inward-opening hatches implemented after previous models had proven hazardous. Originally, the ISS was intended to operate for approximately 15 years. However, its enduring success and unwavering international support have led to multiple extensions. Some of the earliest modules have now orbited Earth for over 2 decades, prompting questions about their long-term reliability. Russia has indicated that it may exit the ISS program after 2025, although it intends to keep its modules operational until at least 2028. NASA, at one point considering retirement in 2016, extended operations through legislative support by 2018, with plans now extending at least to 2030. If commercial space enterprises are not ready to continue the legacy by 2031, NASA may decide to maintain the station even longer. Decommissioning the ISS safely presents a complex engineering challenge. Several options were considered: allowing it to descend naturally, raising its orbit, or orchestrating a controlled plunge into the ocean. The safest approach emerged as a meticulously planned descent into a remote portion of the Pacific Ocean, often referred to as the spacecraft graveyard. Initially, NASA explored using a modified Russian Progress ship to guide the station's final journey, but the plan evolved into the creation of a dedicated American deorbit vehicle. In January 2022, NASA announced that this spacecraft, based on SpaceX's Cargo Dragon, but enhanced with a larger engine and over 40 small thrusters, would launch in 2030 and execute the ISS's final controlled descent in January 2031. This culmination promises to close the chapter on one of humanity's most ambitious and enduring technological achievements in space, a testament to international cooperation, scientific curiosity, and the boundless drive to explore the cosmos.